Okay. Are we ready? Good afternoon. I hope you had a nice lunch and maybe got out in the sunshine. Yay! Sunshine is good. So this session is our second keynote speaker, Sydney Fells, and he's the HCI keynote and happens to be my brother. So he is a professor in electrical and computer engineering at UBC, and he holds the Dolby and Midnet Professorship in Digital Media since 2017. He's also the lead of the Human Communication Technologies Lab, and his little symbol's right there. And I have to say that he's a great brother, all-around good guy, and in our family, he's pretty well the star. Because his research, he's done a lot of pioneering research since he was a postdoc, actually even before that, since he started his PhD, and that was a while ago, and I think he's going to tell you how many years that was. He works a lot in neural nets, especially early on. He does, I see a mouse. It's okay. He's done work in really interesting interfaces for the musical expression and interactive arts, and I think he'll tell you a bit about that. He's doing work in biomechanical arts, and he does a fair bit of work now in the health field, so health technologies. And all this work's resulted in numerous publications in many different venues, GI included. But other ones, Kai and NIME and various others. And he has supervised many, many students which share his passion. I've met a number of his students, and they're very passionate about what they do. So without further ado, I would like to introduce Sydney Fells to give you his keynote address for about 45 minutes or so. Okay, we ready? Go for it.
Yes. Hello. Thank you. Thank you very much, Deb, for that kind introduction. And thank you, everyone, for being here. And thanks to Adrian and GI for inviting me. I really appreciate this opportunity. So today I'm going to talk about the work that's being done at the Human Communications Technology Research Lab at UBC that I've been working on for 25 years at least, and really talk through, the emphasis on this talk really is about how the lab and the research has focused on human experience. And so that theme's going to come up. And while the projects may seem a little disconnected, I'll try and make that argument that by that focus on human experience at the core of what we're trying to understand and communicate in different ways, that's what binds these pieces together, and the contributions being made by wonderful students and researchers that I've had the pleasure to work with. And the privilege to work with. So let's get started here. So what's this all about? It really is about thinking through what is the future of human communication. And we typically think of communication, especially I'm in an engineering department, electrical engineering, computer engineering, in terms of bits and information technologies and entropy of the communication, through the communication channel and that sort of thing. But what I argue is if we look a little bit to the future, it's not so much about the bits, it's what they're trying to represent, which is human experience. And so the interfaces and the techniques to communicate human experiential phenomenon is at the core. And once you think about that, then your approach to some of the interface design issues and the technologies behind them takes on a different flavor. and starts to hit the edges of what we know today in terms of some of the computational methods, and you'll see in some of the biological methods as well. So that translated into the lab's goal really is this notion of effective communication of human experience with information technology PAM. So we're going from from IT, information, to ET, experiential technology. And so once we go down that road, we start to say, well, what's at the core of experience? And from my point of view, it's taking into account people's cognitive abilities and ways the brain works around cognition. The physical, the body is integral to experiential phenomenon, and the emotions, the affect, they're all connected. And so if we start to look at those and say, hey, what do we do for information when we think about information? We do that for experience. So things about how to acquire, analyze, represent, store, retrieve, transmit, communicate. And what I'll show today is the synthesis of some of these experiential phenomenon, and the technologies necessary to make that happen are where a lot of our advances are coming from. And so I'll talk about three main areas of the projects that we're working on. These are the current ones that we're working on. If you check out the lab website, you'll see some of the archive of stuff that's has been done in the past. But today I'll talk about really the focus on what is active right now. So there's the body, I mentioned that already. So this is around how we control voice and how voice and body are connected in speech and body. Then I'll talk about video, and one of my beliefs around the emergence of video as an expressive communicative media. And then lastly, I'll show some fun stuff with Fish Tank VR and 3D displays and teleconferencing in 3D. So that's, and then I'll summarize at the end of that. So let me just start with this ridiculously old video that I still look at, and it's still, I'm still learning from stuff. So I realized that when I did my PhD, I thought I knew what I was doing, but actually I didn't know what it was. It's taken me many, many years, and I still am learning about that. I didn't know what I was doing, and gaining new insights. So I'm going to play that. I know many people have seen it, but there's some new context for it. Okay, so what you're going to see is the Glove Talk 2 video of Sagi Vore reading Sam I Am, the Green Eggs and Ham book. So here it is. Assume the audio is working.
I am Sam. I am Sam. Sam I am. That Sam I am. That Sam I am. I do not like that Sam I am. Would you like green eggs and ham? I do not like them, Sam I am. I do not like green eggs and ham. Would you like them here or there? I do not like them here or there. I would not like them anywhere. I do not like green eggs and ham. I do not like them, Sam I am. Would you like them in a house? Would you like them with a mouse? I would not like them in a house. I do not like them with a mouse. I do not like them here or there. I do not like them anywhere. I do not like green eggs and ham. I do not like them, Sam I am.
So what you were seeing there is Sagiv instrumented with two gloves, one sort of measuring the continuous angles of his fingers. The other one were essentially buttons on his fingers. He had a foot pedal that he could, that had a spring on there. So it's analog. And then a tracker of his right hand in three space, as well as orientation. So lots of instrumentation, mapping that through a machine learned neural network architecture that would map those into, in this case, they were frequencies and amplitudes that were situated in the voice band. And so in his mind, he's playing a vocal tract. So he's playing sound, and that's getting mapped into frequencies and amplitudes. So he didn't have to think in terms of, he just thought in terms of opening his mouth, opening and closing a mouth, and constricting it like a sh, z, v. And these were like little buttons for blah, blah, blah. So that's what he learned to play. It was a lot of effort, 100 hours worth of learning and training the neural networks along the way. For me, the kind of interesting thing that came out of that, though, is, well, it doesn't sound so natural, kind of robotic sounding speech. He was able to be fairly expressive, and he could even sing with this thing, and have regular conversations with lots of nonverbal cues. So, where's that coming from? If this was just a gesture recognition to words or phonemes or something, you wouldn't get that expressive component. And so that has led down in a way of like, well, where's that expression coming from? And how do we keep that capability in terms of the ability for a person to control a complex space? So this research actually is situated in a lot of historical work. So you can go all the way back, and I didn't put it on here, but there's, late 1700s work, but Joseph Faber's Euphonia, which was this talking sort of head keyboard device that was making the rounds. These are the pre-Netflix. What people would do is actually go and see these spectacle things, and it would play voice and speak. And Alexander Graham Bell, who had seen this Euphonia, also created his own version of this with his brother, with these little hand actuated tongue-like thing under, and a jaw that would move up and down. And then electronic versions came later in the 30s. And I want to show you one that is still very influential for me, which is the Voder, which was Homer Dudley and Bell Labs, created for the 1939 World's Fair. And from an HCI point of view, this was a chordal keyboard that was controlling, again, the power spectrum over the range of frequencies of a voice. And the operators would learn to play this funky keyboard with, there's a little wrist switch on there and a foot pedal. So here we'll just see her playing this here. If I can get it to play, here we are.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords. There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
So you get the what they were able to do, and that's 1939 with this interesting keyboard. So in all these, and including the Glove Talk 2, the sound itself does not sound very natural. In fact, the complexity of controlling the voice by shaping the frequency spectra, which is what Glove Talk 2 did, as well as the Voder, turns out to be incredibly complicated, and it doesn't sound that natural, though it does maintain expression, but it's in this robotic. So how do we make it sound natural? seems like a simple question, but in fact, that's a extremely large research program that we've been embarking upon, that has also international people working on that. How to make it sound natural. How can you make it easier to play? That took a year for them, specially trained people. And with Sakiv, it took him quite a bit of effort to learn to play voice and play speech. So some of our underlying belief on that is that if you're controlling frequencies and amplitudes, that's really not in the space that we think in terms of motor control of speech. We think in terms of articulation, in terms of muscles. Like when you go to speak, you're actually activating muscles of your tongue and your jaw and various other components of the thing. So if we could represent it in that space, then the topology between the way your brain thinks in terms of motor control and the way the synthetic one would be in sort of the same space. So that answer to that question led to a fair amount of research, which I'm going to talk about. And then how is this all represented in the brain in the first place? Are there language models imposed upon the motor control? Is there a kinematic chain? These sort of questions. So I'll go into each of these and how this led to things. So, so the first thing was really, how do you get this thing to sound natural? And it is linked to the how to make it easier. So we decided to go down the road of creating a biomechanical model of the human vocal tract that would be controlled by these synthetic muscle activations. And so we were looking for existing software that could do such a thing, and there wasn't anything. There were either articulated bodies or like rigid body system, methods, or there were these finite element packages. But there's nothing that allows you to bring them together, which is kind of what we need for the vocal tract, because if you did this whole thing in finite element, it'd take forever to compute. If you do it in rigid bodies, well, how do you get the lips and the tongue and all the stuff going on with those soft tissues? Because speech, you've got these vocal folds putting sound into this weird shaped tube that your muscles are shaping to get the resonances to sound like speech. And so that's all soft tissue stuff. So, so we built a modeling and simulation environment called Artisynth that allows you to couple rigid bodies and finite elements and other approaches to soft tissue together in a unified framework. And that's the toolkit's called Artisynth. So at the base, there are these sort of components that you can combine together to then create these complex hybrid, tightly coupled soft tissue, rigid body, like bone and tissue models. And then on top of that, we can then model and simulate different function. And so speech is really the one we're looking for. So we built that, and that's an ongoing effort. It can be used for a lot more than speech, obviously, but that was its original intent. So here's just some examples of that combined rigid body, soft tissue modeling functionality that that's embedded in Artisynth. So you've got your classic rigid body stuff, but then you can start to combine those elements with those finite elements. So these are the finite element components. Remember, these can all be coupled together, which is what we're going to need for like modeling the tongue hitting the palate or the teeth. So just showing some of the, it's also an interactive. Oh, and all this needs to run in real time, of course. So those finite element methods need to be extremely efficient because ultimately we're going to control this thing either with our hands or with our brain in some way. Excuse me. So lots of the functionality. A big part of what the philosophy behind it, because of this focus on getting, the voice phenomenon modeled, in real time meant we needed to be able to blend or put detail where we need it and simplify where we don't need it. So lots of scaffolding. So the rigid body acts as a lot of the scaffolding. And then the finite element, you just want that on the soft tissue parts that are really critical for what you're interested in terms of synthesizing. Well, I don't need to play the whole video here, but that gives you an idea, but definitely check it out. So using that, we built this thing called our Frank model, which I know I put functional reference, blah, 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 but really it's Frankenstein because it's been cobbled together from a number of different models from research groups around the world who work on particular elements, and we brought them together, worked together to bring them together into a unified one. And so Frank is the name of the model. It's got structural components, what's supposed to play. There it goes. So yeah, so this is our Frank model. Saw it spinning around earlier. So yeah, it's got the face, the lips, the tongue, rigid body jaw, maxilla. It's got a hyoid bone. It's got vocal, the larynx, the tongue, and all these things are combined together. So the tongue's an FEM model, skin's an FEM, and then there's some texturing on top of that. And all this is now activated by muscle models. So computational muscles. Excuse me. So from that, then we can make this thing move. So here's Scott Moysik's larynx model. So you can see it's moving around. Some soft palate work that we've done. The other important lesson to learn that I've learned about human anatomy and modeling it, I always find myself saying, oh, why don't we do the soft palate? That'll be a lot easier than the tongue. It's like, no, it isn't. Every single component of the human body has its own complexity, and the details are everything. So there's no easy thing in any of this stuff. So that's just showing you some of the function. So for us, now that we've got this anatomy modeled that can be controlled by muscles, we got to get the sound out. So how do you get the sound out of this thing? Well, the sound, of course, is a function of the shape of the vocal tract as well as what the vocal folds are doing. And these things are coupled. So that's typically represented with a model like this, where you got to have the bass, the excitation is called. That's the sound coming out of the glottis, going into the tube, which is your vocal tract, which is being shaped by the muscles, and the sound pressure coming out the orifice, the mouth. It's basically a really funky musical instrument that we've learned to play in a way that some listener understands that music as speech by putting all sorts of constraints on that. But it's a wind instrument. So now how do we get the sound out of there? So there's one-dimensional models which compute very, very quickly, but they do not provide the entire range effectively, nor can you go from this complex geometry easily to a one-dimensional model. And so that's problematic. 3D models, you can get 3D acoustic models, wave propagation, very, very slow. You know, a second of speech can take days and days of computational power. So we've gone down a road of approximating with 2.5D to capture mostly the structure, the acoustic structure, and approximating the 3D parts of it by lumping them. So I'm sure everybody remembers these equations. Probably we're working on them yesterday, but what we're doing is these are the classic wave equations, and those are what we translate into GPU implementation. And these equations are really important because they translate in 2D directly into GPU architectures that can be accelerated. And remember, we want this in real time because we're going to control it. So just to remind you what these things are, so you got pressure, and then the pressure is moving. So you got a velocity vector, and then an input, so an excitation, the thing that starts the sound propagation into the sound domain. you've got boundaries. So where the sound was going to hit is going to reflect or absorb or something like that. And then you have physical parameters, speed of sound and density, air density. So that's what these equations are representing. And all these are put into the RGB A channels of your GPU in the texture maps. And then the GPU can compute these in parallel with each cell and its neighbors, as all you really need to update these equations. And so that's how what you're visualizing there is the pressure wave moving around through a domain and hitting that boundary. And then if you have the pressure wave, and this is all simulating at frame rates of 192,000 frames per second, not 192 frames, it's like 192,000. So it has to update at the audio rates, not the visual rates. So it's very, very fast. And then you use a synthetic microphone, really just reading the pressure at a certain location in your world domain here, and see what the acoustic pressure at that point is. Send that to your sound card, and that's the sound. So that's the idea. Here's a little demo of that. So there's the little pressure wave coming in the center. This little pink thing is the virtual microphone, just reading out the pressure at that particular spot in the world around the excitation. Excuse me. And then if you put a little area, and we can slow the visualization down so you can see the waves propagating. So there's the slowing it down. So you see the waves hitting the obstruction there. And so depending on the shape, you get different resonant cavities and that sort of thing. So that's the underlying development that we created so that we could then just figure out what this weird shaped vocal tract is going to sound like, because we're going to be controlling this thing with muscles. And so to show you that for the 2D stuff, it actually does produce something like speech. So it's capable of reproducing the appropriate spectral structure for speech sounds. And remember, this is all being simulated through a model of an acoustic tube model. Things we're working on to make this work is dealing with the complexity of the shape and translating that into our 2D, or actually our 2.5D, because there's 3D effects that need to be lumped into the equations, because they're only 2D, and that gives us our 2.5D is by lumping the 3D components. So you've got the different shape, you've got the curvature, and confirming that's actually working properly. So our first step is we have to be able to replicate the results of the 1D. So for 1D geometries that are simulated with 2D, it should give the same results. So we have to do that. Likewise, we have 3D simulations that take forever. We should be able to do a reasonable job of that up to about 8 kilohertz of the sound frequency, which is approximately the vocal range. And deal with some of the asymmetries. There's the boundary effects. There's the lip impedance. So there's quite a number of things that all need to be taken care of, and we're well forward along some of those pathways to make sure that the sound that comes out is what a sound of a human vocal tract would sound like, that we can then ultimately control. But you can use this for other things. It's a general purpose wave equation solver. So we've created this thing called a hyperdrum, which I don't know why that didn't just play. Why is that not playing? Maybe it was playing. Hey, that's weird. That's a YouTube video that's supposed to play. Let me just jump to a little example. Yeah, so we got the surface, and you can just draw the contour for the sound wave propagation, and you can give it material properties that are in the drum. And a drum, the drum head is a two-dimensional surface, and you hit it, that's an impact, and the waves propagate out and hit the surface. Well, that's exactly what that wave simulator is actually synthesizing. And so if you just give it drum properties, you get this thing called a hyperdrum. And then you can draw dynamically your shapes and put different sounds in there. And do this all as part of a yeah, that screen is really fast. It just shows you that that's a general purpose solution, even though we are targeting speech with it. So now that we've got that, oh, just a sec, the chair is telling me something. 10 more minutes. Okay. So how do we control this thing? So there's a couple things, obviously gesture and voice, and brain as ways that we're looking at, as well as this apparatus is also used for breathing, eating, and speaking. And so the motor control of like the coordination of that can be used as sort of a scaffold to build the more complex things. But it does really lead to the question, and this is the HCI question, which is, well, how much can a person actually generate? How much information capacity does a person have? And how do we take full advantage of that to control this complex voice articulation? Because that's a very hard problem. It's like playing a musical instrument. So that is how we got to this representation of the closed loop model of the brain is controlling the articulation, creating that moves this vocal tract that produces the acoustic and the visuals. So you see it moving, that a perceiver sees and hears and responds. And that goes back into your brain and trying to understand what's going on. And did you actually understand it? So we're going to try and figure out a way for people to control this thing and within this closed loop system. So there's a number of challenges here, but ultimately you want this bandwidth here. And this relates to pretty much any HCI thing where you're controlling something, whether it's with your hand, with your brain, arms, feet, or whatever, to get the information rate as low, like the information demands on the brain here, as low as possible, while still conveying the information and the meaning of what you're trying to say. So, does Fitts' law apply to speech, right? If it's about information, well, how much information does it take to speak? And, depending you ask, you'll get a different answer. Some say, well, it needs a lot of information. Look at all the different sounds and meanings we convey. On the other hand, other people say, no, it's not very much because, your tongue is inside the mouth and it, you bang control. You just turn it on, it's going to hit the palate. And, maybe speech is a lot of forward control that doesn't really need a lot of precision. So there's this kind of tension between ballistic and feedback control that's going on to, is the listener understanding what I'm saying? Can I tell that I'm making the right sound? All these things are complicated. And so that's what we're looking at is, well, if we do think in terms of Fitts' law, you got your classic, reciprocal tapping task here, and you've got your information rates and index of difficulty being a function of the task. Then you've got, well, what happens if there's like a constraint in there, like a brick wall there? Well, you're a lot faster. So how's that being modeled? It's that infinite width target or something, or big target. It's a little complicated, but it definitely makes it easier when there's these constraints in there. And then what's happening in your mouth when you're trying to speak, you know, if you think of it as unconstrained, I'm making like phoneme to phoneme to phoneme, e, oo. It seems like this, you know, I've got to get the targets very accurate. However, what's going on in the mouth, when you look at what's going on, is there's these constraints that are happening. And they're coming from a couple of different sources. There's the physical constraints. Your tongue's going to hit the palate. So when I go to make an S, my tongue, you feel the sides of your tongue hitting up top there, right? And so, yeah, it's precise here, but the shape is not so precise because it hits the palate. Likewise, you're talking to someone. There's a language model. So as long as they understood, I can kind of go, and they understand you. That was good enough. And so those perceptual constraints really can reduce the index of difficulty of the task space. And then the brain is smart enough, as we know from Fritz's law, to take advantage of the changes in the constraint space to change the motor control programs. So if we're going to create a gesture to speech or a brain to speech interface, we really do want to incorporate those constraints into the space to make sure those are respected, because the brain definitely will take advantage of those. And even further, the brain may even encode those constraints in its own representation of the motor control of speech. So without them, it's going to be much harder. And so that's the implications of that. And so the machine learning is a way to try to match those constraint spaces and investigate that and to see whether the brain is actually representing that. So that's why we really argue that the brain and the body, when it comes to speech, they're really coupled, because the representations need to know about the body and what's going on in the physical world, as well as the language models and the other sensory models. So that's the, if you look at some of the papers that we've been working on lately, is the direction we're going in terms of trying to get machine learning to respect those constraints. And so, so yes, we're looking at that chain of motor control from concept and intention and meaning to the actual movements to a listener and incorporating those constraints. All right, well, that's the first one. There's a wonderful team of people all working on this project together over the years. So I just put a few pictures of them there. So that's the whole brain to speech and modeling of the upper airway and the acoustics and everything coming together to get that speech and vocal experience. So another thing we're working on, so this is, so there's that topic. So then the other thing is video. And I make an argument that video currently is not a first-class citizen of media. And that one of the things we can do as researchers is elevate it to be a first-class citizen. So things that make it so it's a little poor cousin to text is that it's very hard to author. It's hard to do to integrate with, say, your Excel spreadsheets or your Word documents or your text documents. And it's hard to have conversations just through video. Obviously, we know how to talk to each other, but me sending you a video and you responding with a video as a conversational media is only just emerging right now. So we've been looking at, well, what happens when you start to make it mutable, interoperable, and bidirectional? So some of the work was using video in an educational platform. This was happening before the pandemic, so people were not using as much online teaching and video. At the time we were doing these experiments, but we created a system called vidX, this with a lot of Microsoft funding. So we created a prototype that could be used in the classroom, so high enough fidelity that people could use it. And we ran in a number of classes with quite a few videos to see how people start putting some of these features of mutability, interoperability, and bidirectionality into a learning environment and see whether students use it in some way or another and what what works, what doesn't work. Likewise, talking about video, that's that interoperable notion, and also looking at the learning ecosystem, that played a big role too. I was going to give a demo of this, but maybe I'll just play the video. This is our BitX interface. It has mechanisms so that there's a transcript, there's a main viewer, you can highlight items in the transcript, you can highlight things on the film strip, you can make annotations, you can put tags, you can copy and paste the text out. And so just ways to mark up and the video to have a personalized or annotation of the video. There are other things as well, like crowdsourcing usage and that type of thing. But you can add those sort of features. One of the main findings that really came out of it, though, was this notion that your notebook really is the core when it comes to learning. The notebook is the heart of an information ecology, and that there's many sources, and video is being one of them. And video has a hard time being one of them because it's not easy to interoperate. You can't, like getting to a certain location in the video or making an annotation of that certain thing in your notebook, there's no page numbers, and writing time codes is kind of complicated. It's not easy. And so that's where we really got to this notion of where video is failing, is because of that interoperability, and it's very hard to take notes and get back to the source material. Though when it comes to learning, the best videos are the ones you don't have to watch in terms of information. And that leads to other insights about learning from video, because video is slow. So that's sort of the finding there. The other main finding is people talking about video. It's hard to talk about video. And so a paper that Dong-Wook Yoon and Natan Yamad and I worked on is this referencing. So when you're talking about video, there's lots of different content in the video, like the audio, the visuals, if it has closed captioning. And so we built a referencing system here.
Our proof of concept interface illustrates the feasibility of design concepts for type referencing and in situ dereferencing.
Charge can't flow.
But we started late.
Users can create a reference to a snippet of the video by dragging over the seek bar. For users reading a comment, our Insight to Hover and Replay feature can enable them to access the reference contents without leaving the vicinity of the source comment.
So you can see there that the references, when you put a reference to video, it embeds it inside. And so this is that notion of this interoperability again, showing up. So these are the things we argue that video, for it to really become this communication medium, we're going to need to really include those capabilities in it. So anyway, I'm not going to have time to talk about the reference types and somehow we got there, but ultimately leads to this summary, which is, as HCI people, creating the pencil and paper for video really is what we're going to need to allow us to have deeper video experiences and mechanisms to express ourselves through video. And so that's a major theme. So there's, again, a great group of people that are working on this. So last thing I'm going to talk about, because I only have like a minute, so I think I can get through that in a minute, is, oh, where did that go out of its full screen mode? Okay, is this Fish Tank VR. And really one of the main points about this Fish Tank VR is Fish Tank VR is not an immersive VR experience, right? It's about putting virtual elements into the real world, not overlaid on the real world, not like an augmented reality, but so that you can have things that look real, that are virtual, situated in the same space together, and having 3D, so you can walk around them and take a look. So we built this 3D display that was really pushing the boundaries of that. And that's why it's spherical, so you don't have seams and various other things. We did other form factors too. Once you do this, then you can start to explore the types of interaction when you have 3D objects situated in the real world. So when two people are working together on it, it's in the same space. So they have a shared awareness of the same space. This is a 3D Pong game, for example, just to show that, oh yeah, when you share the virtual space in the same way with the real space, then you can actually have these fairly complicated, okay, well, this isn't that complicated, but this ability to have experiences together. So other things that gives are the ability to point from the virtual world into the real world. So Fan Wu will be talking about that tomorrow, as well as eye contact will start to work because it's looking in the right space. So the thing you're looking at in this way is the position you're looking at in the virtual space. And so you get these phenomenon that things really do look like they're looking at you. Excuse me. So putting that all together, one of the applications of that is teleconferencing. So for example, a presentation like this, I'm flat in 2D and not situated in your world and vice versa. But if we put some of this together, these technologies, coupled with some of the abilities to do models or tracking of human bodies, putting them into fish tank VR type experiences, whether it's spherical or flat screen, doesn't matter so much. All of a sudden you can get 3D teleconferencing to work. So we've been working on that. And this is supposed to be a little video that shows what that experience
Hi,
is.
Bebe. How are you doing?
Hi, Cassia. I'm doing
The
well.
idea is
How are
on
you
the
doing
left
today?
side, you've got a person talking to a single camera, RGB, and then on the receiver side, they're going to have this fish tank VR where that head is situated in their same world. And so when you're looking at the eye of the virtual character of the person, the other person, you're actually looking at their eye. It'll look like they're looking at you in the eyes, for example. And to get this all running in real time and low latency and all these things, that's a major research challenge. And the computer vision necessary to this is also a substantial challenge. So we're also building a platform so that you can plug and play different research advances to try and improve and get quality metrics as well as information metrics fairly easily. And so that's what the architecture looks like. Not going to spend too much time on that, but just to let you know that there's this open platform that you can plug and play different encoders and decoders to synthesize. All right, so you know what? I'm just I'm going to wrap up and go through some of the underlying things that we're working on in terms of getting that encoder decoder working. But just to recognize that the infrastructure is so that latency, fidelity, preference, and various qualitative metrics on how well 3D teleconferencing works are part of what this platform is meant to enable. So, said that. So great team of people again working on that. So just to summarize this whole talk is really to make an appeal to people to start thinking in terms of human experience and where people fit and what they're thinking, what their bodies are doing, what they're feeling. These three things are all critical to think in terms of HCI and design and the technologies that support it. It's not just about bit rates. And so when you start doing that, you will push the boundaries of what technologies can do and can't do and lead to unexpected, exciting new projects that have very large ranging applications. And that's been a very effective pathway for our team in my lab. So that's great. So I want to thank again, great team of graduates, students, undergraduates, and postdocs and faculty all working together. Great group of sponsors, industry sponsors, as well as our Tri-Council government agencies. and many partners around the world. I just listed the UBC ones here, but there's a fantastic set of international collaborators that are part of this work. So that will wrap it up for this presentation. So thank you again for your attention. And I will turn on Discord as well so that I can take questions. I don't hear
Okay.
it. Oh,
Thank
there.
you, Sydney. That was wonderful. Lots of stuff going on. So we have a few questions, and we'll begin with the floor, and then if there are others on our Discord group, we'll get you.
Yeah,
Hi,
I'm just
Michael
trying to get
McGuffin. I'm
this-
a prof at ETS. So I have a question about Fitts law. So Fitts law can be derived from models of control systems, and I think these models assume that there's a certain minimum noise in our nervous system. But then when I think of examples of highly skilled motion, like there's this story about Michael Jordan, the basketball player, that he was throwing the basketball at the hoop one day, and he could feel that something was off. So then when they went to measure the hoop, it was 1/8 of an inch off from where it's supposed to be, right? And then when you were talking about speech, I was imagining a young child learning a language. I would suppose this child would get better and better at saying rapid sequences of phonemes. So I wonder what's going on there. Is the child somehow learning to reduce the noise in their nervous system, or are they getting better at generating the initial impulse, or what are your thoughts on that?
Right. So excellent question. So for me, they're all happening at the same time. I personally think the brain is wired to take advantage of all statistical advantages it can find. So if you're a child learning and you're watching the listener, if the listener understands what you're saying, then it's good enough. You don't need to spend more energy learning more. Likewise, if the movement is doing good enough, then no point in spending a lot more time learning that. So that good enough comes from multiple sources of constraints. So language model, motor control, noise in your nervous system, the myelination, as the myelination of the nerve pathways is changing, and that changes very quickly in children as they're learning. Those start to reduce the noise in the neural channels. So you're learning on top of that. Likewise, the muscles here are also changing and developing. And those are also integrated into the neural representations. And all these things help, in my mind, they all help to reduce the index of difficulty so that your learning task becomes easier and easier. I mean, the other thing that we seem to take advantage of is your chewing and swallowing. Like swallowing, there's some argument that speech is really built upon the motions of swallowing. So for some of the core sounds across all humans, it looks really like swallowing plus, and then we vary from there and build representation. So that's why I think that's a very important question as to what the neural representations are to reduce the noise, to get the index of difficulty smaller and smaller.
Okay, great, thank you.
I think we have Betham. Okay, one more question. Sorry, Sid.
I just want to thank you for the great talk, by the way. I just want to get back to your argument about making video a first-class citizen again. So I'm just wondering what you think about like the emergence of platforms such as TikTok, right, that have made video sharing at least a lot more popular than perhaps it used to be. Just want to hear your thoughts on that.
Yeah, absolutely. TikTok is an example of when we start to move away from video as a broadcast medium. And one of the challenges we have to make it a first-class citizen is to make it easy to author. And so embedding structure, a known structure, so that we as a creator can just add to that structure, makes it a lot easier. And there's mechanisms that are doing that, like Canva also provides that. And so I think we'll see the emergence of genre of video content that is structured in a way so that we can very easily create content and author that in a vocabulary that everybody knows what that means, so that there's a video language, so to speak. And
Right,
then
so we
that'll
go
just
beyond
get more
sharing.
extreme.
Yeah, I see. Beyond,
What's
we go
that?
beyond sharing and actually start editing each other's work, that kind of stuff.
Well, that's what Mutable is all about.
Right.
I send you a video, you
Play with
copy,
it.
manipulate, send it back, and we'll have Google video, collaborative video making, all in the video world. And it plays well with text and others, but it has its own world. And yeah, this is what replaces TikTok, by the way, if you're looking for the next big thing.
Thank you.
Thank you. I'll just read one comment because it's not a question. The Live Scribe pen and associate technology might be part of the pencil and paper for video by linking actual pencil and paper to time codes automatically with a question mark. Holy cow. We'll leave that as it is, if that's okay, and we will wrap this up. Thank you so much, Sydney, for your really interesting and fun talk. There's so many things you're doing, and thank you, everybody, for being here. We've got our next session is sketching, and I will just take a bow for you. How's that sound?
Thank you. Thank you. Appreciate everyone's attention.
Hello. Okay. We'll move on to our next set of papers. In the sketching group, we have two great papers for you. The first is Structured Shape Patterns from a Sketch, a Multi-Scale Approach. Do we have the AV guys ready to go here?
Hi, I'm Pauline Olivier from École Polytechnique France, and I will present Structured Shape Patterns from Sketch, the multi-scale approach. This work tackles the interactive sketch-based design of an isotropic distribution of shapes in 2D. From building facade to seaweed to scallopfish and even fibers and cellular organisms, anisotropic distribution of shapes are ubiquitous in nature and artificial environments. Such distributions are composed of banded and fiber-like shapes, and they convey some underlying global and local structures that give them a unique visual appearance. While example-based synthesis have been widely studied in the last few years, only a few methods tackle anisotropic distributions of shapes. The set of methods consists in tackling anisotropic distribution of points. This method usually rely on procedural noise or deep learning approaches. However, they are restricted to points that are not directly applicable to Sketch and are not real-time. For anisotropic distribution of discrete shapes, the method either reduce the shape into a set of sample points or use proxy geometries. However, none of the existing methods handle both bounded and unbounded shapes. They will require an additional step to be applicable to Sketch inputs, and are also not real-time. Extending the Sketch patterns into an extended domain requires formulating a few hypotheses about the user's depiction and perception of the resulting patterns. Our key hypothesis common to most Sketch-based modeling systems is that users see the input as a general view of the distribution they want to create. Therefore, the input is supposed to contain all the necessary information. This leads us to the following hypothesis. Groupings and alignments are meaningful. For instance, the purple fish are meant to be aligned. Repetitiveness is explicit. There is only one vertical seaweed. Non-overlapping shapes should remain disjoint. For instance, fish should not overlap, nor two seaweed should intersect. Following this hypothesis and to answer our real-time need, we built a solution on the novel data structures called superstructure hierarchy. This representation enabled us to encode all the main features of the anisotropic distributions in a compact manner and avoid high computational cost. In addition to these representations, we include the following contributions: profile course analysis to go from sketch to our hierarchy, a course to find synthesis using this hierarchy and the set of perceptual hypotheses. And finally, we integrated this solution into an interactive authoring tool, letting the users test, refine, and combine their design. We built our hierarchy by successively reducing the input strokes into coarser linear structures, carrying a group of strokes that are closest in positions, direction, and alignment. We first clustered bounding strokes into shapes. Then these shapes are simplified into super segment or central points. These elements are then clustered into fibers. Other fibers are extracted from the unbounded strokes. All of these fibers are grouped into supermaton and then linked directions. Finally, we delimit areas along the superstructures to avoid overlaps and plan repetitions during the synthesis. So we have lead ribbons around lead directions, ribbons around fiber matons, sub-ribbons around fibers from fiber-like shapes, and displacement areas around bounding shapes. Unlike most existing approaches, our synthesis methods consist in directly replicating the local and global correlations between the input shapes encoded by our superstructure hierarchy. Starting at the top level of the hierarchy, we take repetition into account in order to clone structures and then generate the allowed areas when the child structures can be extended and then generated. In particular, we introduce a coarse-to-fine adjustment methods to fit the generated element into the allowed areas at the price of slightly bending their superstructures. This process is iterated down the hierarchy until the stroke distribution are generated. Here is the result of our planar synthesis for our sketch input. On this planar synthesis, you can see that we respect the anisotropic distribution of both bounded and unbounded strokes, while maintaining groupings and avoiding unwanted overlaps. Here is another example illustrating a biological phenomenon. The user starts by creating a field of fibers composed of unbounded strokes of different widths. Then he picks the bounded pencil to create individual cells composed of different strokes. This example highlights the use of our system to create a complete sketch inspired by biology. Here you can see a comparison between the input on the left and our expanded pattern on the right. Here is a simple example to illustrate our interactive authoring system. First, the user draws desired pattern, and then it launches the synthesis. By opening the menu, the users can modify the size of the output domain to generate various vector textures. Thanks to our randomized repetition procedures, in addition to the main sketching and texture expansion interface, the user may store and reuse complex shapes. In particular, several input shaped patterns can be interactively combined to create a hybrid one. Thanks to the superstructure hierarchy, the user can select the desired level of hierarchy from two different input shape patterns and combine them to create a brand new input and generate the synthesis. Let's now compare our work with the best existing methods. First, for anisotropic point distribution, you can see that our model preserves the groupings into columns, while avoiding overlaps are artifacts that can be seen in previous work. Moreover, our method does not require any pre-computational stage. We also compare our method with the best classical approach addressing anisotropic distribution of discrete shapes. As you can see, it can be hard to estimate the best model, especially since none method compute metrics with the input. To help us evaluate our solutions, we use our user study to let the users choose between our expanding vectors and the generated ones from Landes and R. For this example, 86% of the users prefer our results. For this one, 77% of users prefer our results. This user study also helps us validate the perceptual hypothesis we introduced previously. We separate the user study into two sessions, one drawing session during which the users need to fill the empty space around the provided samples, and the selection sessions, including the comparison with previous work. Here are the tasks we provide the users during the user study. It's the task we provide the users during the drawing session, and on the right is a sample of their results. First task consists in replicating the bounding shape and avoiding overlappings. The second task was about respecting the groupings and alignments of unbounded shapes, while avoiding overlapping. The third task was mostly about our repetition hypothesis for unbounded shapes. And finally, the last drawing task was about the respective groupings and alignments of bounded shapes, as well as avoiding their overlapping. The goal of this task was to see if users prefer to have overlapping unbounded strokes or not. And the goal of this one was whether they wanted repetitiveness for a singular element or not. The study was conducted with 35 users from 19 to 61 years old. Most of them did not have any training graphics either on the paper or on a digital device. Here is a sum up of our results for our perceptual hypothesis. As you can see, we highly validate H1 and H3. However, H2 is left for more discussion. In particular, during the drawing sessions, users mostly extended the strokes and did not replicate them. Here is a table presenting the performance of our methods for our examples. It can be observed that overall computational time takes less than a second. To conclude, through the use of our superstructure hierarchy, we were able to propose a multi-scale approach to encode the anisotropic property of an input sample and extend it into an extended domain. You can find the user study following this link. The demo should be available soon. It can be a useful extension to let users have more control, in particular by being able to choose between perceptual hypotheses or even prioritize them. And an interesting future work would be to extend these methods to more various shapes, such as branching. Thank you for your attention.
Let's thank the authors. Okay, so I believe we have time for a few questions. Is anyone? I believe there's one on the Discord. Is there anyone in the audience that would like to ask questions? Okay, well, while you guys are thinking, I'll ask a question. So, there were 3 hypotheses that you had in your work. I'm curious how difficult do you think it would be for artists to add their own hypothesis, like adding repeated things in circles, or should go in circles, that sort of. Yeah, so you had the 3 hypotheses, like repetition, overlap, but there aren't. But I suppose like an artist might want to say, well, if I have multiple repeated patterns that go in a circle, that they should continue in some circle pattern. And is it possible to extend your method with more hypotheses that are custom?
Yeah, like it would be like the current version is just like stick to the 3 hypotheses. So if perhaps it can be a way to, like, I guess, like in the future version, to just draw perhaps some hypotheses to sketch and have the system like recognize what the user intends by the sketch hypothesis, and have the system like propagate this hypothesis throughout the synthesis. But
cool. Okay. Thank you. Okay. So I guess this was, I guess a similar question. So from the Discord, do you support circular aligned patterns?
Not yet.
Not
like,
yet. Okay.
We're just like, we're based on linear structures, so it's really just like, so either line or either like waves or continuous, and but we just like stick them to some linear ribbons, so they're not only like on this part.
Okay. Could you give more details on how you seam the fibers at the edges?
Okay, I don't understand what those seams, the fiber and the edges means. Extend?
Maybe, yeah. That would be my interpretation. Yeah. How do you extend the fibers at the edges?
So the edges, like our fibers, are like we get like 4 type of fibers. So we got the linear fibers, which is like extended like as a line. We got the wavy fibers, and for that we just extend in like mirror-like. So we just like reverse and alternate the reverse mode like that.
Cool. Okay, so I have one more question. If there's no question in the audience, so what would happen if you try and prevent intersections by essentially bending the fibers? If an artist does something really catastrophic, like has extreme curvature where they would connect like unbounded fibers or unbounded curves that can clearly overlap in the future, how do you like untangle multiple extreme curvature overlap? I guess I'm sort of mumbling my words here, but if you end up with a problem with a lot of overlap, how do you solve that?
So we get currently we get some priority over like the position of lines, like how close they are clustered together, and also their direction. So at some point we get these thresholds that decide which fibers are part of the same higher structures, and so whether they should overlap or not. So either we're considering this overlap. So we get this threshold, and we get also some kind of like debug mode when the users can just like change the sliders in order to decide whether they want to cluster some fibers together and not, and have so the wanted or not wanted overlaps appearing.
Cool. Great. Okay, so we should move on to the next talk. Let's thank our speaker once again.
Thank you.
Hello everyone. I'm Renwei Zhang from the University of Tokyo. I'm here to give the presentation about our paper, Energy Hair, Sketch-Based Interactive Guide Hair Design Using Physics-Inspired Energy. The capture of real human actors as virtual actors has become popular in the entertainment industry owing to the advancement of multi-view stereo techniques such as the light stage. With these techniques, virtual actors, for instance, digital animals, are almost indistinguishable from the real actors. However, capturing hair is difficult. That is because sometimes a strand of hair is thinner than a pixel. It would be challenging to capture hair automatically. Also, hair has high specularity, which means hair's color may differ rapidly between neighbor views. Another reason is tight occlusion for hair in images. It is difficult to estimate the shape of entire 3D hair strands based on outside appearance. Therefore, conventional multi-view stereo cannot be directly used for hair. Actually, hair design for virtual actors is still a manual task. However, it is not so easy to manually design physically reasonable hair. This video shows our design using Maya Xgen. We can see that during the design, hair is floating in the air. And hair is going under the skin too. Also, the view needs to be changed frequently to design plausible hair strands. And there are a lot of works that have tried to improve these circumstances. Among them, some work focused on detailed hair capture. This work generates highly detailed hair geometry, but it is still difficult for artists to design. The hair simulation has models such as the mass spring model and superhelices model. However, it is not intended for use in interactive modeling. Some sketch-based hair designs consider interaction, but it is still difficult to edit the 3D shape of guide hairs. Therefore, we want to input users to the sketches and generating 3D hair strands. However, directly using the 2D sketch information for 3D reconstruction cannot work because of lacking the depth. To solve this problem, we introduce physics-inspired energy so that it is possible to reconstruct 3D hair strands from 2D sketches. Here is the overview of our work. Energy hair. Our workflow includes two parts: the offline pre-computation and online design session. The offline pre-computation uses real human images to reconstruct a 3D human head as well as multiple viewpoints, which would support users' 2D sketches. Also, we pre-compute necessary data to suggest sketch for users. The online design session uses the energy minimization method to balance the 2D user sketch and 3D hair strand. We support 3 operations for users to interactive design guide hair. When users left-click to draw a stroke for one single strand of hair, the sketch suggestion system will show a red line to suggest the shape of the current designed hair strand. By right-clicking, users can drag the strand anywhere they like. During dragging, the editing hair strand may appear in different colors representing physical validity. From pink to blue, hair becomes more and more physically plausible. Well, to make hair look physically reasonable, users can press the middle scroll button to use sketch relaxation, which would decrease the physical unreal part of the current hair strand. But how do we achieve these tools? Well, let me introduce our method. The key is to optimize an energy function, W plus K. W is the energy potential energy. V devotes 3D hair strand, and theta devote physics parameters. Elastic potential energy describes the physical plausibility of the 3D hair. And the key is sketching energy. It penalizes the difference between the input 2D sketch and 3D hair strand. First, let me go deeper into the sketching energy K. K prime is the sketching energy of a single hair. Under each viewpoint, each hair has 2D elastic potential energy and distance energy between sketch U and hair strand V. For distance energy, instead of naive way to compute the distance from points on hair strand to sketch line, we use spline representation to replace the polyline. Ours will be the distance from the points on the hair strand to the spline curve of the sketch. Finally, we sum all viewpoints energy to obtain the K prime. Then the other energy of our method is elastic potential energy. W prime is named for a single hair's energy. It also contains 2 parts. 3D elastic potential energy computes hair strands stretching and bending energy, which means this kind of energy is only with a straight rest configuration. Then we also add the gravity and penetration depth from the head to our elastic potential energy. We also have an automatic sketch suggestion system. This system requires images of a real human head. Then we compute the orientation field by applying the Canny filter. Because we do not need such a high-resolution orientation field, we blur and downsample it. The orientation fields represent the hair strand's directions from 0 to pi. Also, we introduce the similarity field to identify the hair region roughly. This field shows the average difference between one pixel's orientation and its neighbors. The darker pixel is, the more similar with the round neighbors. Here, I will show the procedure of the sketch suggestion system. For the current suggestion mount point, the suggestion sketch will grow under the direction of an acute angle and keep on growing until it meets a point that has a similarity beyond the threshold. Then we will get the final suggested sketch from the mount to the end of the hair strand according to the input image. Okay, that is all for our method. To show the efficiency of our spline representation for distance energy, we compare the results of our spline distance with the naive distance. Through the videos, we could see that ours can successfully achieve the global minimum. This is the video sample of our energy hair made by an artist. More results shown here. For the limitation, our physics model is simple, only with straight rest configuration. Users can make straight hair easily, but curly hair is difficult to design. In the future, we plan to include additional physics-related parameters such as curliness in online optimization and develop a real-time preview for hair results, not only guide hairs. Thanks for your attention. Please feel free to give your questions.
Okay, thank you. Okay, so we'll have a few minutes for questions before breaking for coffee. There's a hand up in the back. Okay, while you walk up to Sheldon, I have a question. So I can imagine an artist would be interested in doing this on maybe one character in a movie, but maybe less interested in having to do this for each character. I'm curious if you've thought about doing like transferring between heads. Like once you've drawn on one, can you use the same tool to transfer the guide hairs onto a new person's head geometry?
So thanks for your questions. So you mean whether our reconstruction result can transfer from one head to another head?
If an artist traces the hairs on one person's reconstructed head, could you take those traces and transfer it to a different reconstructed head without the artist having to redraw it on the new head?
I think we can transfer from one hand to another different head, and that is because the different will be only the energy functions result. So after transfer that, we can also optimize the function again and get the result. So I think artists will not re-sketch the guide hair again.
Great, thank you. Do you have a question in the audience?
Hello? Oh, good. Thanks, very nice work. I really like the physics-based model that you're using to do the the hair strands. So if I understood correctly, this is based upon the discrete elastic rods work from 2008. Is that right?
Yeah.
The physical model. So it seemed in a lot of the examples you're using straight hair, but this model can support curvature as well. So have you thought about how to extend the work so you can do curlier hair, curvier hair?
The reason that we cannot do the curly hair perfectly is that our energy function, although we use some energy function like the elastic discrete elastic rod, but our physics-based elastic rod, our physics-based energy function contains only the bending and stretching energy. So that without the curliness energy. So that's the reason why we cannot deal with the curly hair perfectly. So if we want to deal with the curly hair, the obvious way is to add another energy like curliness. So this kind of energy will help our tool to deal with the curly hair.
Cool. Yeah, I think that would be good to try, because I think the physical model you use already supports that. And this is a sort of a tack-on question. So I think from the physical modeling side, that would work. But have you thought about how an artist could sketch curly or fuzzy or frizzy hair? Because it has a lot more detail and complexity than sketching straight hair, which might be easier for an artist. But have you thought about how to actually have an artist sketch that type of hair, and then use it as an energy function that you could optimize your the hair strands that you're generating?
Sorry, I don't know whether I understand your question. Is that the
I can simplify it. Have you thought about how an artist might sketch curly hair?
As I imagine that the curly hair is something like so in the 2D screen, to draw the curly hair sketch, I think is almost I think it's the simple as the curve. Yes, is that.
Okay, yeah. I just think it would be difficult. It might be more complex than that with a 2D sketch, because of the additional complexity, the additional dimension that you have there, right? Anyway, thank you for your presentation and for answering the questions.
Thank you. Thank you for the question.
Okay, are there more questions in the audience? All right, I have one more question before we break. Okay, so towards the end of the talk, you showed the head model with a much fuller head full of hair than the original guide hairs. Can you explain to me how you fill it in with some sort of tracer hairs, or how did you get that full head model with such sparse guide hairs?
So thanks for the question. So I mean, how to make the full hair strands using several guide hair?
Yes, yeah.
That is, I think that is the some tools already implemented in the commercial software. That so the full head of hair strand will be guided by the guide hair, and that kind of technique will be done by MyXGen. So the MyXGen only require the guide hairs input, and then the neighbor's hair strands around the guy hair will be interpolated to several different, several similar hair strands. So.
Okay, great.
Yeah.
Thank you. Okay, any
Thank
last
you.
minute questions? No, if not, then let's thank our speaker and we'll go for a coffee break. Thank you.
Thank you very much.
Okay. All right, so we have a half-hour coffee break, although we only have like 20 minutes, and then we will come back for the Detecting User Abilities paper session. Thanks, everyone.
Okay, very good. I think we're ready for our next session entitled Detecting User Abilities. We have 3 presentations and they are all virtual.
Hello, I am Raniero Laraganuno, and I am the primary author for Detecting Mild Cognitive Impairment through Digitized Trail Making Tests Interface. So this paper relies mostly on the trail making test. It is a paper and pencil version, a neuropsychological examination, where you connect dots in ascending order. So part A has the subjects connect dots in numerical order. Part B alternates between numbers and letters. So 1A, 2B, 3C. Relies on frontal lobe function and tests for executive function. It's sensitive to a wide variety of temporary and permanent cognitive states. And so what we're going to do is we digitize this and we try to use machine learning binary classification to determine automatically if somebody might have a subtle impairment called mild cognitive impairment. So the Montreal Cognitive Assessment Test is a different kind of test. And the reason why I'm mentioning it is because for 2 reasons. It is using the short version of the trail making test B, but it also is being used frequently as a ground truth because of the breadth that it takes. So that's what we're using here for our ground truth score. In addition to template matching recognition systems, there are geometric features for classification. They are using machine learning algorithms that was work started by Rubin in the early 90s, and that was kind of expanded on by researchers like Stahovich, Long, and Paulson. Digital sketch recognition has been used to measure cognitive state, including development and decline. So Kim identified development in infants by analyzing simple shapes drawn. Davis and Muller digitized the clock drawing test, which is a different kind of paper and pencil exam. Zam found a correlation between Parkinson's disease and drawing spirals and with a digital pen. When it comes to TMT specifically, Damin digitized the work, the trail making test, and kind of attempted to segment the sketch based on the location of the pen, because the TMT is ideally a single long line that kind of made things a little difficult to accurately make a representation of the test in a machine learning classification model. So data segmentation is pretty important in this kind of context. So they did compare against a more severe form of cognitive decline, which is technically kind of easier to do. And on they also used as a ground truth a telephone interview for cognitive assessment and the frontal assessment battery with a 44 to 67% accuracy. And those two ground truths were a little less common in the field. They also did not classify the lines themselves, just the entire test. So what we wanted to explore is if we enhance the segmentation method and integrated a lot more features, would we get at least a comparable result? And can we classify for a more subtle condition? So this is kind of what we get at with our research question. So what we developed was a universal Windows platform app designed to digitize the paper and pencil test. And we recreated the test layouts exactly the way that they exist with a center that we partnered that helped us get all of the test subjects. We did things like keeping track of time, but not showing it in the background because we wanted to just kind of have the application, even though it's a digital application, we wanted to recreate the paper as much as possible. So the whole thing was as static as we could make it. There were some additional interface tools for analysis. You can replay tests in real time. Some of the features got visualized, and those were mostly for the neuropsychologist side of things. So we didn't do a UX study on these, but we would like to in the future. The data that we get out of this is time series data. It is sketch-based, time-stamped XY coordinates, and the pressure data for each sample. Output to a CSV file. Then we used Python for text input and parsing, Pandas for data management, and sklearn for machine learning model and classification. So we wanted to talk a little bit about the data processing. We did a constant distance formula resampling. Then we normalized for line rotation, and the normalization was mostly done because in digital sketch recognition, machine learning features take into account direction. But in our case, direction is pretty hard coded to where the person is instructed to go. So we wanted to make sure that if there were line deviations, that there were deviations that weren't supposed to be there. So we normalized it by having all of the dots go from top to bottom. And so, for example, in line segment 22 in here, you could see that they were going in one direction and they had to switch. So that was actually something that the user did as a mistake. So we wanted to capture that. Lines are segmented in 2 different categories. In our case, travel lines and search lines. Lines were already segmented by Damin, but they were only segmented by locations you can see in the top. If the pen drifted away, they would still get segmented as outside, even though that's not really what they were doing. So what we wanted to do was define it as a state. If they were below a certain threshold, or they were like constantly returning to the dot they had already visited, they would still be called that they were in that search state because they didn't know where to go. So this is the kind of behavior that we wanted to capture. So in our case, the pen moved from 1 to 2, then they started moving in that direction. They realized they weren't going the wrong one. They stopped themselves and returned to 2. Then they continued to drift, sometimes moving outside of the dot, returning to the dot. Then if user finds the next dot and leaves, they would end the search state. The other kinds of lines are travel lines. They're labeled in blue. They're basically any straight line that is connecting the dots. You're not required to be above the threshold to be when you needed to be in X to be able to exit the search state. But when you fall back down below it, you would enter a separate hesitation state. That means that we are capturing that you were going in one direction with confidence and you stopped yourself. So that was kind of something that we wanted to capture as well. So data segmentation is kind of going to look like this internally at the end of it all. Then we're going to look at the classification models that we used, the features that we use for a classification model. We have the Rubine features. These are the 13 Rubine features. In the interest of time, I'm not really going to cover them, but they're covered in the paper itself. They describe everything from how quickly the line is drawn to the direction of the line. Features 14 through 18 that we included in our model are additional geometric properties added by Long in 2000. They are described there and in more detail in the paper itself. The second half of the Long features are described here. Everything from openness to the log of the total length, base 10, and the log of the aspect ratio and that kind of thing. Features 25 and 26 are called NDDE and DCR. That's normalized distance between directional extreme and the direction change ratio. Kind of in short, they're described extremity, so to speak, of the maximum and the minimum direction values. So they can be used to distinguish things between just a polyline and a more of a curved shape. And DCR is kind of like attempting to describe the same thing. The next two features are kind of interesting because they're Fitts law and steering law. These are kind of features that are not usually lumped with digital sketch recognition, but this is kind of an idea that we had for the trail making test specifically. It is a model to describe psychomotor behavior, and the distance is D, the width of the target is W, and we just included that as kind of the Fitts law index of performance. As feature 27. Feature 28 would be similar, the steering law. I'm not going to cover that a whole lot in this particular presentation, but it's covered more in detail in the paper. Finally, we have a set of features that we are included for the novel features. So we included the hesitation feature that I mentioned before with the pen lift time, average pen pressure, and standard deviation. Features 33 to 36 is the average pen speed, deviation of the pen speed, line ratio, Fitts and steering. So talking about the machine learning model itself, we removed feature collinearity of 0.9, and this is kind of what we get at the end of it. For constructing the model, we use a standard 90-10 split for 10-fold cross-validation. We train and evaluated according to MCI using MoCA scores as our ground truth, and the parameters are kind of outlined in the figure. So we're going to be talking about the data collection a little bit. We partnered with the Center for Translational Research in Aging and Longevity here at the university, Texas A&M University. They handled the recruitment and that kind of thing. Anything below a score of 19, they were considered worse than MCI. Anything above 26 were not MCI, so kind of healthy in that respect. And 19 to 26 were considered MCI. The screening was successful. Participants were asked to start at 8 a.m. and then we just gave them both of the exams. This is kind of like the breakdown of the demographics. Total of people were 21 MCI and 16 non-MCI with an average age of 71.43 years. So covering the results with 3490 line segments for travel lines. Worst to best, we had the Gaussian naive Bayes classifier followed by the decision tree, K-nearest neighbor, linear regression, then SVM, then LDA, and finally the best performing was random forest. And these are all fairly common in digital sketch recognition, which is why we picked them. Comparing against dominant results were not quite one-to-one, partly because they compared against the entire trail making tests versus what we did, which was not between line segments. They also did not report F1 precision or recall, but for them, it was the worst performing was J48 and the best performing was naive Bayes. In terms of feature importance, they were kind of flat, but I did want to point out that average pressure for both travel and search models were like fairly important. So it was kind of an interesting thing to note there. When it comes to the noisiness of the data, there was a lot of noisy data in that like certain people who had MCI were still not making mistakes when creating some of the lines. So they would be kind of considered healthy, but at the same time they would be labeled MCI. So that kind of threw off the classification a little bit. So a much higher number of lines, much higher than 3490 lines, would be able to help us with making a deep learning model that can then help us with an unsupervised model there. So they divided between healthy and neurologic, which we divided as considerably, which they considered considerably impaired. But in our case, it was actually, we had to work with a much narrower definition of that. So Damin did a per test classification. We did a per line classification, which we believe is a lot more localized, is a lot more granular, and it kind of like works in the favor of this information-rich line information that we got from the digital sketches themselves. So there's a lot of things to improve, like UX study with subjects, UX study with proctors, et cetera, and that kind of thing. So to reiterate a question 2, as you can see on the screen, we kind of come to the conclusion that using MoCA as ground truth, classifying with a milder form of cognitive impairment, and we're also able to improve on the line segmentation methods. We believe that that was a fairly significant contribution to the problem. So these are our authors, and now I can take some questions.
Ooh. Very good, thank you. All right, any questions from our audience? Okay, well, I have a question. Did you use the TMT test with your participants? Did you compare between the paper-based version and your digital version in terms of results? You know, you were talking about
the
milder.
paper-based.
Yeah, go ahead, sorry.
Sorry. Yeah, the paper-based version was basically identical between both of them, and we tried to design it so that they would be as close as possible. Because I was working with a center that was using the same protocol for a separate, they were collecting data for a separate thing, so we couldn't insert both of the tests at the same time, kind of as a comparative measure. So I tried to mitigate it as much as possible by just having it as close to the paper as much as possible, but we didn't have like a second paper-based test for us to compare to. But one thing to note is that I did have, in a previous study that is unrelated, but also still published at GI, interestingly enough, was a separate test that also did a paper version and a digitized version of the same test in the same tablet, and they actually were very, very similar in terms of performance. So we think that it was very similar. We did not think there were any issues there.
I have another question.
Sure.
You suggested that it was your test, the digital version, was able to, if I'm interpreting this right, interpret or diagnose milder cognitive decline. And I'm not sure what you mean by that, and I'm not sure whether that is worth doing.
Sure.
Maybe you could just highlight that a little bit.
Yeah, absolutely. So mild cognitive impairment is a condition that is the precursor to more severe forms of cognitive decline. So that's kind of the condition that is found in that happens just before Alzheimer's. And it is characterized by a cognitive impairment that is a little more accelerated than if an elderly person's might be, because everybody's cognition declines just a little bit as they age. But the primary purpose is for early detection. And so for the longest time, there have been many efforts in neuropsychology to try to suss out early signs of cognitive impairment that might lead to Alzheimer's disease, dementia, and other kinds of conditions and diseases. So we kind of fitted into that space, particularly because MCI, mild cognitive impairment, is not characterized by things that can be easily found. So a person might be able to completely live life as they might want to, but their very subtle signs might only show up with a battery of tests such as these. So we try to implement a machine learning based model on time series data so that we can try to find subtleties that might otherwise be more difficult for a clinician to determine.
We have a question in the audience.
Okay, I have a question.
Yes.
I was just wondering, how do you define mild cognitive impairment? Is there a scale or a number? I know MoCA has scales within which you say, okay, this is mild cognitive, this is high level impairment. So in your algorithm, do you have a similar scale? And my second question is, how would you differentiate symptoms between mild cognitive impairment and other impairments? Because there are quite a few symptoms like vision-related impairments, like Charles, I don't know if you're aware of them, but there are impairments or symptoms which are common in mild cognitive impairment and other neurological impairments, which make it very difficult to diagnose early stage impairments or mild cognitive impairments. So how would your algorithm know that this is exactly leading to dementia or other forms of impairments? Thank you.
Absolutely. That's a great question, and that's one of the things that we have to take into account. So one of the things that we wanted to do, or that we were seeking out, was to specifically look for, we specifically sought out a data set that would give us pre-diagnosed by a clinician, a group of people who already had mild cognitive impairment. So we used the definition we kind of like shortened it to the definition of the MoCA, like between 19 and 26, just to have like a numerical threshold for our label. So that's kind of how we arrived at that. And to make sure that we weren't taking into account things like, what if their vision is failing and that's why they're performing poorly? What if they're any other thing that they might have? That's what we were looking at in terms of the data that we were describing. Now, that does mean that we would need to get a lot more data in the future to have people who have those kinds of conditions that might, in this model, throw off that model to make it think like it's MCI when it actually is not MCI. It might be something else. So the answer is we need a ton more data. As the paper kind of alluded to in the presentation, also alluded to, it took about a year and a half worth of studies to get as many as we could, just barely below or barely above 30 something people. So we actually, there's a large challenge in getting very valuable data such as this. So we wanted to make sure that at least the data that we were getting, absolutely they did have MCI, so that at least our binary classification could take that into account.
Very much.
Thank you.
Okay. Well, thank you, Renario.
Thank you.
Very nice. Thank you. Okay, we'll move on to the next one.
Hello. I'm going to present our work on automatic detection and correction of asymmetric weight distribution utilizing electrical muscle stimulation. An outline of the presentation. I'll take you through the motivation for the research, related works, and a user study conducted to evaluate the performance of our automatic AWD correction approach. Posture is the manner in which we support our bodies in everyday activities like standing and sitting. The alignment of our body parts with the correct muscular tension plays a crucial role in maintaining healthy posture. Repetitive actions such as prolonged standing, sitting, and lifting, and use of computer systems are often the main factors contributing to repetitive strain injuries such as slouching, asymmetric weight distribution, wrist extension, and neck cradling. AWD is mainly characterized by weight-bearing asymmetry on the legs. AWD commonly occurs during prolonged standing conditions, leading to imbalanced hip loading and lateral pelvic tilts, which may lead to increased risk of falls, knee, or ankle injuries. Nearly $90 billion are spent annually in USA alone for the treatment of repetitive strain injuries caused by poor postures. The current intervention technologies only deal with detecting and alerting the user to self-correct their poor posture. These systems rely completely on the user's willingness and ability to correct their poor posture while performing highly engaging tasks. Electrical muscle stimulation can be a way to correct poor posture through involuntary muscular contractions. This presents an opportunity for development of automatic poor posture detection and correction systems which do not disrupt the primary task the user is engaged in. Electrical muscle stimulation is a non-invasive technique for delivering electrical stimuli to the muscles, nerves, and joints to invoke involuntary muscular contractions. Traditionally, electrical muscle stimulation has been utilized in pain management, for the treatment of chronic muscle strains, acute muscle spasms, and in rehabilitation to regain muscle strength and normal movement post-surgery. Recently, there has been an increased interest in EMS-based feedback in the HCI domain for delivering more immersion through muscular contractions based on computer feedback in virtual reality, augmented reality, and mixed reality applications. This presents an opportunity to develop interactive and adaptive wearable interfaces for posture correction. Currently, HCI research has focused on utilizing EMS for activity training, input-output interfaces, and immersive technologies. This presents a gap in research for design and development of a smart wearable intervention device for autonomous asymmetric weight distribution detection and correction utilizing electrical muscle stimulation. As asymmetric weight distribution is mainly characterized by uneven leg loading, we developed a physiological feedback loop utilizing load sensors and electrical muscle stimulation for detecting and subsequently correcting AWD. We utilized a Wii balance board that contains load sensors to constantly monitor the user's weight balance ratio on each leg to detect an AWD condition. When AWD was detected by our system, electrical muscle stimulation is applied to the tibialis muscles to invoke an involuntary muscular contraction that generated a physiological response of restoring balance through a counterweight shift approach. The graph illustrates the activation and deactivation of EMS correction feedback when an AWD left-leaning condition was detected and corrected for a participant during the study. Initially, under a balanced posture condition, the EMS on the left and the right leg remained deactivated. A timer with a preset time threshold of 2.9 seconds was activated when the user's balance ratio gradually increased and crossed a preset balance ratio threshold of 1.2. The preset balance ratio threshold of 1.2 translates to a balance ratio of 44.5 to 55.5. Upon completion of the timer, if the balance ratio still remained above the threshold, the EMS was activated to apply a stimulus on the right tibialis muscle. This stimulus invokes an involuntary muscular contraction which generates a counterweight shift to restore balanced posture. The EMS was deactivated immediately after the balanced posture was restored. A correction response time of 1.2 seconds was recorded between the activation and the deactivation of the EMS. To determine the time and balance thresholds for improving the robustness of our AWD detection system, we collected data from 10 participants performing 10 common actions during prolonged standing activities. These actions were slight lean left or right, sway, balanced, extreme lean left or right, calf raise, lift left or right leg, and scratch leg. The balance ratio patterns for each of these actions are illustrated. The leaning conditions present unique balance ratio profiles which allow for its detection. We employed a grid search to find the time and balance ratio thresholds that optimize the accuracy of AWD detection. We found that at a time threshold of 2.9 seconds and a balance ratio threshold of 1.25, our system achieved high accuracy of 96% for AWD detection. The balance ratio of 1.25 translates to a left to right or right to left AWD balance ratio of 55.5 to 44.5. We conducted a 2x3 mixed design experiment with 36 participants. The within subject factor was the feedback type, audio, vibrotactile, and EMS. The between subjects factor was the application type, the quiet standing, and the mobile game task. In the quiet standing task, participants were required to stand quietly while they played an engaging battle royale game called PUBG Mobile in the mobile game task. We hypothesized that EMS feedback would deliver the fastest AWD corrections across all three feedback types and that users would perceive EMS feedback to be the most accurate. We also hypothesized that EMS feedback would deliver an equally comfortable experience with no more task disruption than the other two feedbacks it was tested against. Prior to starting the experiment, participants were required to complete the consent process and the pre-questionnaire. Participants were then required to stand on the Wii balance board for calibration, and the electrodes were placed on the tibialis muscles and calibrated for optimal EMS intensity for correcting AWD posture and restoring balance. The participants then performed a 3-part experiment and completed the post questionnaires after each part. The participants were required to complete all 3 parts, the audio, vibrotactile, and EMS feedback sessions, in either the quiet standing or the mobile game task. Each part was 15 minutes in duration with a 5-minute seated break between each part. For the audio feedback modality, in both tasks, when AWD was detected, an auditory notification leaning left or right, please correct imbalance is presented to the user, and the user was required to correct their AWD posture until a second notification stabilized is presented to the user. For the vibrotactile feedback modality, in both tasks, when AWD left or right was detected, a vibrotactile notification is presented to the user on the opposite leg, and the user was required to self-correct their AWD posture until the vibrotactile notification stops, indicating a restoration of balanced posture. For the EMS feedback modality, in both tasks, when AWD left or right was detected, EMS feedback is automatically applied on the tibialis muscle on the opposite leg to invoke an involuntary muscular contraction, generating a physiological response of counterweight shift and thereby restoring balanced posture. EMS was deactivated when balanced posture was restored. We conducted a repeated measures ANOVA on the correction response times for modalities and applications and found that EMS delivered significantly faster corrections with an average of 1.31 seconds in the quiet standing task and 1.33 seconds in the mobile game task. We also conducted repeated measures ANOVA on the user perception data and found that EMS and vibrotactile feedback were perceived to be highly accurate. We also found that EMS feedback delivered an equally comfortable user experience and no more disruption than the vibrotactile and the audio feedbacks. Participants also reported shared responsibilities with a mean ranking of 2 in the quiet standing task and 1.72 in the mobile game task. Participants further reported that they found the use of EMS feedback for posture correction to be highly interesting, with a mean ranking of 6.33 out of 7. Nearly 55% of the study population reported that they preferred EMS feedback for AWD correction, and more than 80% of the population reported that they would purchase an EMS-based wearable intervention for AWD correction. In conclusion, we demonstrated our automatic poor posture detection and correction system for asymmetric weight distribution. We found that EMS delivered significantly faster corrections in comparison to the traditional feedback mechanisms and was perceived to be highly accurate, equally comfortable, and no more disruptive in the different contexts it was tested against. Therefore, EMS-based feedback shows promising potential to be developed into smart wearable intervention technology and could be a useful alternative or inclusion to existing environment health and safety guidelines for mitigating risk of workplace injury and improving employee health and in preventive health care. Thank you for your time. Please let us know if you have any questions.
Hi, Ravi. I bet everybody here sat up straighter. Yes? During your talk? Okay. Do we have some questions? All right. How about from our virtual audience? I don't know. I can't tell. Okay. Then I have a couple of questions. Why did you choose the tibialis muscle to stimulate? Why not some of the other ones that are also involved in posture correction or in posture maintenance, like the glutes or the hamstrings or something?
So we tried different muscle combinations, and what we tried to achieve here was to invoke a counterweight shift response or reflex from the user. And we tried the tibialis muscle, we tried the quads, we tried the hip muscles. The hip muscles seemed to work well, but it was very, it could be like uncomfortable to put it on users. And we tried the quad muscles, but it was only like, it was causing more of a standing up straight rather than shifting the weight. So that's why we went for the tibialis muscle, which was bringing the user back automatically to the balanced posture through the counterweight shift approach. And if you look at the graph in the operation, it shows like the little bit of damping that goes on after the weight shift has happened. So that's exactly what we were looking for, to shift the weight and, and then the electrical muscle stimulation turns off. So the user is free to adjust or readjust his balance posture and stay in the balance posture for a little more time, or maintain the balance posture now that they're aware of what they're doing.
I was thinking more of the feet, but okay.
Feet could be a little bit uncomfortable, especially because it has EMS produces the haptic. It has the haptic component that gives a tingling sensation. So some people might be a little more sensitive to that sensation on the feet. So.
Okay. How about another question? I have one more, if that's okay. In terms of the comfort, I think one of the problems that we always found with vibrotactile stimulation is that it's about 25% of the people are just not comfortable having vibrotactile stimulation at all, anywhere. So did you find that there was a larger number of people who just didn't like the vibrotactile in either situation, and that the audio was preferred because they just didn't like to have stuff on their skin?
Yeah, so the vibrotactile, do you mean the vibrotactile component of EMS or the vibrotactile feedback itself? Because we tested audio, vibrotactile, and EMS feedback separately.
Both.
Okay.
Vibrotactile feedback anytime for anything tends to be uncomfortable.
So, yeah, that was one issue there. But with the vibrotactile feedback, just with the haptic motor modules that we used, it used to make this auditory sound that the buzzing sound that people felt it was unnecessary, or they didn't like that feeling. So there was that, and the vibration that it produces is a little unnatural. So they did not like that part of the vibrotactile feedback. And in the EMS, the vibrotactile feedback was definitely it made the users aware in a way that they have done an asymmetric weight distribution posture. So they said that even though it has that little haptic component to it, they were happy that they could do their tasks, especially in the mobile game tasks. They could continue playing their game while the system automatically corrected them. But in the quiet standing tasks, they did not mind because they had nothing to do. So they were, they felt fine with it. So.
Okay, then Ravi, we will let you go. Thank you very much.
Thank you so much.
In this video, I'm going to talk about our work on using deep learning to detect motor impairment in early Parkinson's disease from touchscreen typing data. This work is a collaboration between the HCI lab at Stony Brook University and the University of Chinese Academy of Science. Sophia Gu is a high school student conducting summer research at SBU. Parkinson's disease is a chronic neurological disorder that progressively causes significant physical and mental impairment and decreases the quality of life. PD is now the most prevalent movement disorder in older adults. It affects more than 1 million people in the US and more than 6.3 million people in the world. Symptoms of early-stage PD can be mild, and clinical assessments require frequent lab visits. However, changes in patients' motor system between visits cannot be tracked, and frequent lab visits increase the financial burden on patients and their families. Therefore, designing mobile tools for remote monitoring of PD symptoms has attracted a lot of attention. With the rapid development of mobile computing, using smartphones to measure movement-related metrics of PD becomes promising. In particular, Previous research that detects motor impairment of older adults via analyzing touchscreen interactions with support vector machines has shown good results. Inspired by previous work, we explored 4 deep learning neural network models in classifying PD patients based on their soft keyboard typing data. Our investigation shows that deep learning is promising in detecting early PD motor impairment using touchscreen typing data, and the proposed LSTM-CNN model is promising in performing such analysis. We formulated the problem as a binary classification problem on touch time series. Given a sequence of touch events generated during the user typing on the touch screen, our goal is to predict whether the user is diagnosed with PD or not. For user I, his or her touch event sequence is denoted by vector xi, where each component is a d-dimensional feature vector collected at time t. We also used a label yi to indicate whether the user is diagnosed with PD. In other words, yi equals 1 indicates the ith user is diagnosed with PD, while yi equals 0 means the user is free of PD. Our goal is to predict the label yi for any given input xi. We investigated 4 deep learning models on classifying PD type sequences: the LSTM, 1D CNN, CNN LSTM, and the LSTM CNN models. We proposed a LSTM CNN model as shown in the following figure. It consists of an input layer, a masking layer, a 2-layer stacked LSTM, 2 convolution layers each followed by a max pooling layer, a flattened layer, a dropout layer, and 2 fully connected layers. The input to the network is a t by d dimensional vector where t is a fixed number of time steps. The output of the network is a value p that representing the probability score that the subject has PD. We also considered 3 other options. We configured the CNN-LSTM model to contain 2 time-distributed convolution blocks, a recurrent block, a dropout layer, and 2 fully connected layers in sequence. In convolution blocks of the CNN-LSTM model, convolution is applied to raw feature vectors at each time step. This architecture is appropriate for time sequences that have a spatial structure in their data dimensions, such as the 2D structure of pixels in an image or the 1D structure of words in a paragraph. We also included the 1D CNN model as the 3rd option. It contains 2 convolution blocks, a flattened layer, a dropout layer, and 2 fully connected layers. We used the same internal sizes as in the convolution blocks of the LSTM CNN model. It is capable of detecting local patterns in the temporal axis and extracting features based on those temporal relations. The LSTM model is the LSTM CNN model without convolutional blocks and the flattened layer. We included it as an option to evaluate whether adding a CNN block after LSTM would improve the performance. We evaluated the performance of the 4 model candidates on 2 existing touchscreen typing datasets and compared them with the SVM-based method. The first dataset is a Tian et al. Smartphone typing dataset. It contains data from 102 subjects, where 35 of them are PD patients and 67 are age-matched healthy controls. We used the 2266 touch inputs collected from typing on a custom QWERTY keyboard. Each touch input consists of a touchdown event, where a user lands their finger on the touch screen, and a touch-up event, where the user's finger takes off from the touch screen. The raw data includes touch point pixel coordinates, time steps, pressure, and measurements from the accelerometer and the gyroscope. In addition to the raw features collected at each time step, we also included information summarized in the bottom table and used a normalized 36-dimensional feature vector as the input to the models. Here, ht is the hold time, which is the time difference between a touchdown event and its corresponding touch-up event. FT is the flight time, which is the time difference between a touch-up event and the following touchdown event. To train the network, we used the Adam optimizer and the binary cross-entropy loss. In this video, I'm going to talk about our work on using deep learning to detect model impairment in early Parkinson's disease from touchscreen typing data. This is promising in performing such analysis event, where the user's finger takes off from the touchscreen. The raw data includes touch point pixel coordinates, time steps, pressure, and measurements from the accelerometer and the gyroscope. In addition to the raw features collected at each time step, here HT is the hold time, which is the time difference between a touchdown event and its corresponding touch-up event. FT is the flight time, which is the time difference between a touch-up event and the following touchdown event. To train the network, we used the Adam optimizer and the binary cross-entropy loss. We performed leave-one-out cross-validation to obtain user-independent results. Specifically, for each pass, the data of one participant was used as a test set, and the data of the remaining 101 subjects was used as a training set. We used a sampling with replacement method with 1,000 bootstraps to define a ROC distribution, from which we compute the means and the 95 confidence intervals of the AUC values. The figure shows the ROC curve distributions. The solid curves are the mean ROC, and the bands are the 95% confidence intervals. We also calculated sensitivity, specificity, and the F1 score for each model using the closest to 0-1 criterion. The 4 neural network models have similar or better performance compared to the SVM method. In particular, the LSTM-CNN model outperformed other methods in terms of AUC, sensitivity, specificity, and the F1 score. The second dataset is the Ecovakis et al. In the clinic dataset. The dataset was acquired from 33 subjects, where 18 were PD patients and 15 were healthy controls. It consists of smartphone typing data and the clinical evaluation for each subject. For the typing data, they collected the normalized pressure and the time steps at touchdown and touch-up events for each touch input on a quartile of keyboard. We used pressure, hold time, flight time, and the first derivatives of the pressure over time as the 4-dimensional input vector. Since the in the clinic dataset only contains 33 subjects, we reduced the complexity of the 4 neural networks to avoid overfitting. We removed the first LSTM and fully connected layers and decreased the hidden size in the LSTM to 32. We used the following hyperparameters to train the model and performed the same analysis as in the first dataset. The table shows the results of the 4 models versus the SVM method. The LSTM-CNN model performed the best in terms of sensitivity, specificity, and the F1 score, while the 1D CNN model performed the best in AUC. The figure shows the LCM model outperforms other models in distinguishing PD from healthy controls given the optimal decision threshold. Our results show that deep learning is still promising in PD classification from smartphone typing data, even with limited information. In conclusion, we investigated 4 deep learning models for detecting early PD model impairment from smartphone typing data and showed their effectiveness compared to the SVM model on 2 datasets. And we proposed the LSTM-CNN model as a promising structure for using deep learning to perform such analysis.
Okay. Hi, Sophie. Thank you.
Thank you. Do you have any questions?
Questions? How are you AI people? All right, I have a question.
Sure.
Your training data was pretty small. for
Yeah.
AI. How did you deal with that? How did you account for that?
Yeah, that's a great question. We use some techniques such as the dropout layers and then reduce the size of network, and we train for only small amount of time and something like that.
Okay.
We also perform, sorry. Yeah, we also performed the leave one out cross validation because we have only data from 101 subjects. So we use the data of 102 subjects, and we use the data of 101 subject as training data set, and use the left one as the testing data set. And we did this for 102 times. In that way, we don't need to like split the whole data set into training and testing, which will further like decrease the number of data we have, right?
Okay. Wait, there's another question. Go.
Okay, hi. Thanks, Sophia. What is the relationship between typing on a smartphone and Parkinson's disease?
Yeah, sure. Sorry, my name is Yan. I should have clarified it.
Sorry.
Sorry about that. But it's like people with Parkinson's disease will have the motor impairment. Like when they're typing, maybe their, for example, their finger will trembling a little bit, which will create different interactions. Touch points and the pressure and the values from like gyroscope, something like that, different from non-diseased people. So we're trying to detect those subtle motor impairments signs from like the results of the smartphone typing, like the data we collected, they collected from the smartphone typing, yeah.
But don't we all have, don't we all have different ways of typing? So how do you differentiate, you know, even in terms of symptoms and Parkinson's disease? Different people have different symptoms. Sometimes you cannot even detect the tremble or the shake, and they may be diagnosed with Parkinson's disease. So how does your system or method detect those differences? Like sometimes when I am typing on my smartphone, my hands are trembling for various reasons. It may be nervousness, it may be I'm stressed about something. So how do you take those things into consideration?
Yeah, actually, if a person, thanks for this question. It's a great question. And if a person like for example, who have other illnesses or other, for example, mental impairment that will make that like the typing different from like non-diseased people. In that case, we're not able to differentiate those from the. It's not like we're not able to. It's like we didn't conduct any research or experiment on that topic, but I think it's a great idea and it worth future research. Thank you for this question.
Thank you.
I'm sorry. I think we're going to have to move on to the next session. Sophia, thank you very much for your presentation and answering questions. Well done. Okay. Okay. Sheldon's coming. We have an early career researcher award to provide, and Sheldon's going to start.
Hello. There we go. Welcome everybody to the last talk of the day. This is going to be an award talk. I'm pretty excited for this one. Manila Sava, who is an assistant professor at Simon Fraser University in British Columbia, has been awarded the Early Career Research Award by CHCCS, which is awarded to outstanding early career faculty members in Canada in computer graphics, HCI, and visualization and related fields. And it goes without saying that Manolis has made significant contributions already so early in his career in several of these domains. So Manolis has been an assistant professor since 2019. He also holds a Canadian Research Chair in computer graphics. And you may have already used some of Manolis's work, or rather the data that he's produced as part of his work, because he's helped to develop the ScanNet dataset as well as the ShapeNet dataset, both of which were awarded dataset awards at the SGP conference. As well, he's recently released a platform for doing embodied AI research called Habitat, and in general has made very significant contributions in the areas of 3D scene analysis, interpretation, and embodied AI. Manolis Sava, very happy to have you here. Oh, by the way, and I should add that I know Manolis because he's helped us so much this year, because he was the chair last year of GI, and he's been a huge help to us early on, especially getting started in planning and preparing for this year. So congratulations again, Manolis. I'm really looking forward to your talk.
Thank you for the kind introduction. Let's see.
Let's see how it works. One. You have this display. Let's just disconnect them. Yeah, okay.
How about now?
Okay, go here. Now at display setting. Didn't work, right? Sorry for the technical difficulties. We'll be soon. Yeah. This one. This one. Yeah.
Just a couple of technical difficulties, everybody. Bear with us.
I'm very sorry for that.
Seems to be recognizing it fine.
Yeah, but it's like the look of just again. One more resolution. Yeah. So just keep this one. Just let me 1 second.
How about now? There we go. Okay.
That looks like it's working. Great. Take it away, Manolis.
The trick was the refresh rate. All right. So once again, thank you so much for the kind introduction. And thank you for the award. I am honored and humbled to to be receiving this award so early in my career. This is a fairly informal talk. It's fairly high level. I'll try to provide an overview of a number of research projects from my career and try to extract from it a historical perspective with some lessons that I learned. And hopefully some of those lessons will resonate with some of you in the audience. So to start, I'd like to acknowledge all the people who helped me on my journey, who supported me, inspired me, and helped me to grow into who I am as a researcher. And frankly, especially the students who did all the hard work. I am very much a product of my environment, and these great people deserve most of the recognition for everything that I will talk about today. So let's go back to that somewhat peculiar title from my first slide. It says, "From real to virtual and back again." This title describes the different areas of research that I went through in my academic journey. And hopefully it will make a little bit more sense as we go through the talk. To make it clearer, let me try to sketch out that journey a little bit as a sequence, first of the institutions that I've been at, starting as an undergrad at Cornell, doing a PhD at Stanford, a postdoc at Princeton, short period at Facebook AI Research, and now as faculty at SFU. But also, let me sketch out in a schematic view the areas of research that I encountered on the way. The symbols here represent different areas of research, and hopefully they'll make a bit more sense as we get to each part. So let's begin. And here's my beginning. My beginning as an undergrad at Cornell was actually in physics. I was a physics major, and I started out doing research in a lab that was working on ultra-low temperature physics. This was a lab that was trying to take measurements of oscillating nanomechanical devices at near absolute zero temperatures to understand the quantum mechanical effects. Very low temperatures. And this required some fairly arduous empirical measurements. I vividly recall working in that lab. Once a graduate student in the lab snipped the cable the wrong way, and then we had to restart an experimental setup, roll back 2 weeks of preparation time to cool down again from the beginning to be able to take measurements. So very hard work. In that lab, I was tasked with designing and fabricating a so-called microwave resonating cavity. It's in the bottom left of that diagram there. It was used as an amplifier to measure the electrical signals coming from this equipment that was close to absolute zero. And in doing that, I dabbled a little bit with CAD modeling. I designed these parts, copper parts, that we used to fabricate this microwave resonating cavity back in 2007. And this really sparked my interest in computer science. I really wanted to learn more about the technology that enables people to do this kind of CAD design, the software that enables this. And so I looked around and I decided to take an intro. Oh, okay, volume is good? Yeah, okay. Yeah, I looked around and I decided to take an intro to graphics class in my third year. This was taught by Steve Marshner, who's one of the graphics faculty there. And I was hooked. Graphics was this fascinating combination of physics, math, and computer science ideas. And something that Steve said in that class in the beginning, I think for the very first lecture, stuck with me. Graphics is math made visible. That really, stuck with me over the years. So I approached Steve and asked if I could do some research in graphics. And that was really my beginning as a computer graphics researcher, as an undergrad. I started by doing research on capturing and rendering in real time bidirectional texture functions, BTFs. And this actually also involved quite a bit of empirical work. At Cornell, there was this gonio reflectometer setup, 2 robotic arms essentially that allowed one to position a light and camera around an object of interest and take pictures of that object of interest from different illumination and viewing directions. And so again, I spent quite a bit of time in the lab taking images of woven fabrics, capturing that data, and then compressing it and rendering it. So graphics research was also hard in that way. I thought computer science would be less empirical, but I found my way to another empirical kind of research topic. So these were the thoughts that were going through my head as I was graduating from Cornell and going to Stanford to start a PhD. And at the time, I was becoming more and more interested in the modeling side of computer graphics rather than rendering. My thoughts were coming, actually, I think they were described fairly well by this quote that I really like, resonated quite strongly with me from Richard Feynman. What I cannot create, I do not understand. And so I really wanted to dive deeply into modeling and being able to generate all these cool representations of 3D objects, 3D scenes, and so forth. And that was my mindset. And so I went to Stanford. I started there. I was fortunate to have Pat Hanrahan as my advisor there. He's one of the nicest, most positive researchers that I know. And those of you who know him would probably agree. When I was starting and asking for advice on how to approach, just getting, hitting the ground running and getting started doing research as a PhD student, his advice actually surprised me a little bit. He said, just go talk to everyone in the lab. Spend the next couple of months and talk to everybody in the lab. This might, may not seem initially surprising, but for context, Pat's lab at the time was quite large. More than 20 PhD students, postdocs, visiting researchers. Initially I was thinking, that sounds strange, spend 2 months just talking with people instead of actually doing work. But I went ahead and did that. And out of those conversations, actually, very nice things came out. So one of the people with whom I talked was Matt Fisher, who was a more senior student there in Pat's lab, and who was also interested in modeling, and specifically 3D scene modeling. He also had dabbled with designing scenes using CAD software, and he thought it would be cool to work on projects that make this easier. So together we worked on this project where we represented scenes as graphs, right, with objects at the nodes and edges representing spatial relationships, and then applying a graph chronoformalism to establish similarity between parts of scenes to other scenes, to say that, this nightstand with a lamp on it and a clock is similar to this other nightstand with a lamp and a clock in another scene, so that we could retrieve, similar components and replace them and make 3D scene design easier, more efficient. Another, set of conversations that I had that led to some really neat ideas was with Daniel Ritchie, who was a PhD student there as well at the time, and who had just finished a project on design by example with Scott Clemmer, one of the HCI faculty at Stanford. And Daniel was thinking, would it be a good idea to try to design 3D scenes by example? How about that? So I thought it was neat too. And together with Matt, we worked on a project where, the input was a set of examples of 3D scenes, and the output was variations on those examples. Generate new arrangements of these, desks with monitors, keyboards, and so forth, based on a small set of examples that are provided as input. Both of these projects arose pretty serendipitously in chats and conversations with these folks, with these other students. And so I think this is the testament to the value of just talking with people. I took that advice actually and applied it more broadly too, not just in Pat's group, but also with others too. At the time, Jeff Herr was one of the HCI visualization faculty at Stanford. I had a series of conversations with him, and he pitched this idea to me of there's so many visualization images online that are not really following good design principles. They're not that great. Can we do something to improve them? He introduced me to Manisha Agrawala and Fei-Fei Li, and together we worked on this project to try to understand and redesign visualization images. For those of you who don't know the name, Fei-Fei Li is the originator of ImageNet, and I learned a lot from her about the power of community data sets. This will be reflected later on in the talk. So in this project, we collected an image data set representing specifically visualizations, charts, histograms, things like that. We analyzed that, classified into types using a machine learning approach, and then we redesigned input images into alternative versions that follow better visualization design principles. This is, I think, the first project where I really realized that, oh yeah, it's really important to have this, the data set backbone to support projects that take this approach of learning from data. And shortly after that, I also went into a little bit of a foray into the language domain as well. Angel Chang, who was a PhD student in the NLP group at Stanford at the time, and her advisor, Chris Manning, we got to talking about how to turn language into visuals. People use language to communicate, so it would be great if we could take language and produce visuals out of that language. So a fun project that we did first was this project on keyword generation, where the idea is that we can select some set of keyword words that are useful mnemonics for people learning, say, a foreign language or something like that, and that are highly visual, that evoke, very strong visual imagery. And we showed that, with this kind of system to generate, sequences of these keywords, you could improve retention for people learning a foreign language, say, a German speaker trying to learn an English word or something like that. And then probably due to my influence and interests in 3D scene modeling, we worked on this other project on text to 3D scene generation, where the idea is take as input a sentence describing a room, like this one with a chair and a computer on a desk, and then produce a coherent scene out of that. So here too, I learned a lot by my interactions and working together with Angel and Chris about the value of community data sets and consistent benchmarking. This was really big in NLP at the time and not so big in, I would say, relatively in computer graphics. So those were some forays, but coming back a little bit to core 3D graphics, I also had the fortunate opportunity to talk with Leo and work with Leo and some of his PhD students. At the time, Qixing Huang, Hao Su, and Eric Yi were PhD students in Leo Gibas's lab at Stanford. And the conversations essentially were driven by this, what I recall as a ambitious statement by Leo, that it's time for the ImageNet of 3D data. Now is the time to create the equivalent of ImageNet. Data sets back then, 2013, 2014, were not that much in vogue in computer graphics. It was not very much a glamorous thing to be trying to do. So we tried to be ambitious from the beginning to try to convince the community that there's value to big 3D data. And so we had this really ambitious plan that we were going to create this thing called ShapeNet that would have 3D objects in it, annotated with all sorts of things, including symmetries, parts, materials, other physical properties, lots and lots of things. It was a very, in its conceptualization, it was a very ambitious initial effort. And concurrently, this was, as we were starting to work on this was also an NSF proposal. It was actually submitted twice and rejected twice with not very encouraging words. Interestingly, it was this contradiction between, it's too ambitious, and also it's not novel enough, to just be doing this for the community, which is kind of baffling. And we also didn't really have a very good, publication venue in mind. So in the end, what we did is we scoped down a little bit. We said, okay, let's categorize and align a whole bunch of objects and release them to the community. Let's create a data set and put up a technical report on arXiv. This was in 2015. And the rest is history. I continue to be surprised by how many people are using ShapeNet to this day. So while this was happening, I was also invested in understanding and generating 3D scenes. And in talking with my advisor, Pat, I was trying to clarify, okay, what should be my focus in terms of 3D scene understanding. I kept coming back to, this, like generation of 3D scenes, ability to understand them. And Pat's advice was to think about this in a human-centric way, to remember that we all live in a human world, that scenes are made by people for people. The structure of 3D scenes is such that we can do the activities that we need to do in them. We design them in that way. This was great advice, but it stumped me for a little bit because it was not easy to get data at scale of 3D scenes, especially if you wanted to also have this human element in them, if you wanted to have people, doing actions in those scenes. So I wasn't really sure how to proceed, with this kind of trajectory. Fortunately for me, at the time, Matthias Nissner was starting as a postdoc at Stanford in Pat's lab. We got to talking, and what he said to me is, reconstruction works. Depth-based, RGBD sensing-based reconstruction works. You should just use it in all your projects. He's a passionate person, and he really believes in 3D reconstruction, and he sold me on 3D reconstruction. So as an outcome of those conversations, we worked together on this project called SceneGrok, where we went out, reconstructed a few rooms, and then we also captured observations of people using those rooms. A person coming in and maybe sitting down and using a laptop and so forth. And we used that data to then take an input scene and analyze it. Say, okay, where in this scene can different actions take place? Where can a person sit down and work with a laptop? Where can a person read a book and so forth? And as a follow-up to that, we also took a generative slant to it and used the same kind of data to generate these examples of human activities, a little 3D scene around the person, exemplifying what it means for a person to be watching TV. Here's how the person is sitting in a couch, here's the TV in front of them on a coffee table, and so forth. So with continuing interactions with Matthias, again, as I said, he's a very passionate person, believes strongly in RGBD reconstruction. I was convinced that RGBD datasets are a good way to go. And so along with Angela Dai, who started there as a PhD student and was interested in collecting data to improve reconstruction methods, and Angel Chang, who was interested for different reasons because she wanted to ground natural language to 3D scenes, we got to another dataset effort where we developed a software pipeline based on iPad devices, went out to a bunch of rooms in the real world, and our goal was to capture 1,000 rooms, try to collect 1,000 rooms from the real world, and then to annotate those rooms, to endow them with semantics. Here's where all the objects are. This initially seemed like too ambitious of an effort. 1,000 rooms sounds like a large number. But in the end, I think it somewhat panned out. So joined by a few others, we also extended this kind of approach to house level. The Matterport 3D dataset was a year later, was annotating scenes at the entire residence level, multi-floor residences, multiple rooms, objects in them, and so forth. So both of these were, I would say, largely unglamorous projects, at least while we were doing them. Tons of manual effort, countless hours, inspecting objects and rooms and so forth. And it was at the time, I would say, not obvious to us that they would be well received. Other than a dataset contribution, our fears were that there was no clear intellectual contribution to these kinds of efforts. And in retrospect, I would say we probably shouldn't have been that worried. So, if you see a gap in your area of work that asks for a research data set, I would say go for it. Don't worry too much. So this brings me to the next chapter of my journey. This was around the time where I had graduated from Stanford, and I was well into my postdoc at Princeton. I was thinking about next steps, and things took an unexpected turn. This was started by essentially a hallway conversation at a poster session. And I've titled this chapter, this stage of my journey, as Graphics for Embodied AI, or Where Are the Eyeballs? And I'll explain in a little bit what I mean by this. So in this stage, Tom Funkhauser, who was my host at Princeton for my postdoc, invited me and also Angel, who was a postdoc there too, to go to a poster session event at Intel. And there we got to talking with Vladlen Koltun, who was a research scientist at Intel at the time, and his postdoc, Alexei Dosovitsky. And Vladlen told us something interesting. He said, there's this cool work right now from DeepMind and other machine learning and AI labs using games, 3D computer graphics to train AI agents to play the games, right? To play Doom or to play Quake or to navigate, in a game level and go from one point to another. And these brilliant ML and AI people are treating graphics as a black box. Give me game A, I'll train an agent on that game A, and it will do very well on game A. And he was trying to pitch to us that, that's not ideal. It would be good for a graphics person to provide a more flexible empirical platform than a prepackaged game for an ML or AI researcher to be working with. So we were convinced, and together we started working on this project that we called MINOS. This was an acronym for Multimodal Indoor Simulator. And the idea here was pretty simple. We took our recent dataset work, Matterport 3D specifically, and we designed this software platform where you could simulate this visual navigation through some houses. You could have this notion of an embodied agent, something robot-like, moving through the space, going from one room to another, and looking for objects. And the multimodal aspect was communicating that you could simulate lots of things beyond just RGB pixels. You could have simulated depth sensing. You could have semantics like here's all the objects that are seen in the frame. You could even simulate contact forces, other things like that, many modalities. Again, I think this started out as a little bit of too ambitious of a project for its own good, in that we took in all these modalities and said, we're going to do everything. We're going to do audio even. And it was hard to digest. So we were met with some initial disappointment when we tried to submit this for review to a robotics audience. And the reaction was, OK, this is all just simulated. Where are the real robots? Why should I care about this? Does this have any application to real life? So what we did is we scaled back our effort a little bit. We open sourced this as a software library, and we put up a technical report on arXiv, which may not seem like the best outcome, but this led to another serendipitous event, which was actually quite pivotal for my career. And this is the event. Dhruv Batra and Jitendra Malik, who were research scientists at Facebook AI Research, saw this, and they said, we saw MINOS. Come work with us, and we can make this even better. Let's spend a little bit of time doing this at Facebook AI Research. And this was the genesis of the Habitat project. They convinced me to postpone my start as faculty for 6 months and go to FAIR, work with them for a little bit, and work on this project, on Habitat, where we extended ideas from the earlier project, from MINOS, and we demonstrated that with careful software engineering for the 3D graphics components, you could push throughput. You could have high frame rates, which is a valuable thing when you want to scale experiments that require lots and lots of experience for machine learning and artificial intelligence. And really, this was essentially a graphics as a service for AI. This was the idea. And it enabled some pretty fascinating experiments to become practical. In this follow-up work here, training these agents that perceive an environment and navigate in an unseen house from one point to another with massive amounts of experience. Here, the title is 2.5 billion frames, which is roughly equivalent to a decade or so of real-time experience in a house or houses. you could get to things like superhuman performance at, efficiency at navigating to say, you're dropped in a previously unseen house, you're told to go to, a bedroom that's 15 meters to the northeast or whatever, and then getting there in kind of the most optimal path, close to, 100% of the optimal path. Was quite surprising. Here, I'd like to pause for a minute and make a bit of a broader point. This connection between graphics, 3D graphics, and AI, I think, it brings some very interesting systems challenges and also much potential for impactful work. And the reason I think is this. This is a very different use case than the traditional use case of graphics for human consumption. There's no longer any human eyeballs that are consuming these visuals or other modalities that are being simulated. Instead, there's a neural network that takes fairly low resolution input and in the ideal case, does so at extremely high throughput at tens of thousands of frames per second in parallel with many heads consuming that kind of input, say from a number of environments. And that includes also non-visual modalities, other things beyond just RGB pixels that you would show to a person on a screen. So this, I think, could benefit from a top-to-bottom rethink of the graphics system infrastructure specifically for AI consumption. And I think there's much opportunity here to have impact and do good for the world, generally speaking. There are staggering amounts of compute that are being consumed right now by AI and ML researchers, some subset of those consuming these kinds of rendered graphics outputs from synthetic 3D environments. Any inefficiencies can be very, very, very wasteful and bad for the world, generally speaking. So getting closer to today, after spending some time at FAIR, I started as an assistant professor at SFU. And here I want to very briefly talk about a handful of our recent projects that I think represent directions looking forward from today. Very briefly, just a few projects. Here's a recent project where we try to scale up this acquisition of 3D interior environments by addressing one of the pitfalls of active depth-based reconstruction. Those of you who have worked with that technology probably know that mirrors and reflective surfaces are very, very bad. They lead to catastrophic failures, right? Reflections of the depth signal are very bad. Things like those completely erroneous points past the mirror above the kitchen sink and so forth. So this project with a simple neural architecture detects mirrors in scans and then corrects the estimated depth values, leading to much more stable reconstruction results. In parallel to this, project tried to reduce the need for active sensing entirely by relying more on floor plan and sparse photo collection data of the type that you find on real estate websites. You go on a real estate website, you see a floor plan of a house, you have a few pictures of bedroom, kitchen, living room. This is what it looks like. So here the idea is take that as input and then extract out something that represents the 3D architecture, including fixtures of this house, and apply some textures that are inferred from the parts of the photo so that you can create somewhat of an abstraction of this environment and then potentially use it for those kinds of embodied AI experiments. Our hope is that this can lead to much higher volumes of 3D interior data. Another recent project tried to address the challenge of creating big data sets of articulated objects like the glasses and the cabinets that you see here. And while it's now fairly easy to get volumes of static objects, this kind of data, realistically articulated 3D objects, is less common, and it's still very hard to author manually. So here the idea was to design a domain-specific language where a novice user can semi-automatically annotate articulations, motions for 3D objects at scale from a data set like, say, ShapeNet. And this kind of work, I think, can be beneficial for enabling the next generation of 3D graphics for embodied AI. Because a big thing right now is handling scenarios that involve some sort of interaction with an articulation of objects. Like, for example, here, this mobile robot that you see going to the kitchen cabinet, opening it, taking out a box of snacks, and then moving it to the kitchen table. This is from the Habitat 2.0 project, which relied on a manually authored scene with these kinds of articulated objects. And again here, the goal of this project was to demonstrate that with careful attention to the software engineering of such a system, you can achieve high throughput, you can enable much higher volumes of experience. But even despite that, the gains, I think, don't really translate to having solved these kinds of problems. There's a plot here that I want to briefly show. It compares the success rate on the vertical axis of a bunch of different methods at controlling this simulated robot. On the horizontal, there's the number of pick and place actions that you must do as a robot. Pick up an object, move it somewhere. And note that this is just a single room. There's no containers, no opening, no closing. Just go pick up a mug, put it somewhere else. Go pick up something else, put it somewhere else. All the methods that are in solid colors here have no ground truth and so must work from raw perception. And all of them trend to zero very quickly. So despite what popular press may say about the imminent AI apocalypse and robots taking over, I don't think we're anywhere close to that. And lastly, this is just a quick plug. If you're interested in this area of work involving embodied AI, I invite you to participate in an ongoing challenge that we're organizing at CVPR 2022. This is the Multi-Object Navigation Challenge. As a participant, you develop an AI agent that is in an unseen house and has to navigate from one object to another, to another, to another as efficiently as possible. Check out the website if you're interested, and feel free to get in touch as well. So I'd like to end the talk by quickly reflecting on my journey and trying to distill 3 lessons that I took away from my journey that I think may be valuable, especially for the more junior researchers in the audience. Firstly, my advisor, Pat, knew what he was talking about when he said, talk to everyone. Much of the work that I believe this award recognizes would not have happened if I did not explore this interface between research communities and talk with all sorts of people in different research areas. Things like ShapeNet arose from an interest in graphics and 3D modeling, and also being exposed to this community data set mindset from computer vision and NLP. The SceneGrok and PyGraphs projects emerged from this interaction between RGBD reconstruction technology and research and the human-centric thinking. And lastly, this combination of graphics and AI, graphics as a service for AI, led to the simulation projects, Minos and Habitat. Secondly, sometimes good ideas may be too early. Both ShapeNet and Minos encountered trouble initially, but it's important to persevere. Eventually, good work will find success. And then lastly, there's someone out there who can probably appreciate your work. Even though you may not think so at times of doubt, it may not be who you thought initially it would be, but a good idea probably has a target audience that will appreciate it. So again, keep your resolve and persevere. Nowadays, I'm fortunate to be at a place where these 3 lessons are fairly easy to implement. The visual computing and robotics faculty at SFU are vibrant, welcoming, and energizing set of folks. And it's been amazing to see the growth of this group in the past few years. So if you're ever in the area or you're interested in joining us, definitely don't hesitate to get in touch. And before I conclude, I would once again like to acknowledge my mentors and close collaborators who really deserve most of the recognition for everything that I presented today and who have helped propel me and put me where I am today. I unfortunately could not even fit everyone on this slide, and I apologize to those who are not visible, but rest assured you're near and dear to my heart. So once again, I'm honored and humbled by this award. I hope you enjoyed this overview of my journey through different research areas. I hope you found connections and ideas that are interesting and inspiring for your own journey. Thank you once again, everyone, and I'm happy to answer any questions.
Thanks very much, Manolis. And by the way, I forgot to give you your plaque. It's right here. Congratulations.
Thank you. Thank you.
Are there any questions from analysts? I have a question. You mentioned that it was you were doing data sets before it was cool. Like you were doing this when it was very risky, and as you said, it was a lot of effort to go collect this data. And so I imagine, in addition to just collecting it and acquiring this data, there's also a lot of prep work to package it for consumption by different communities. So do you have any anecdotes to share about that process, or any advice to give about that process?
Yeah, that's a great question. It's not just the collecting and annotating, but preparing something for public consumption in a way that it can maximally be of benefit to a research community, or maybe even a broad set of research communities. That's a lot of work. And one thing that I found is that there's this point when we think we're done, and that point is typically optimistically at 50% of being done, usually. So I don't know if I have great advice for it, other than to say that just know that that is the case, and that it requires a lot of effort and iteration even. It's kind of many data sets are a living artifact, right? They evolve over time too, and so they require dedication in the longer term. It's not just, oh, we did it, we're done, forget about it, kind of situation most of the time.
At a certain point, do you sort of give it over to the community? It sort of becomes its own thing, its own living, breathing thing that you've sort of given as a, Does that happen?
Yeah. That I think is the ideal outcome, where the community kind of latches into it, and people do things that you never would have anticipated, never have expected, that are very valuable, right? They augment what you did in ways that you could not have foreseen. That's I think the best kind of outcome for a data set effort.
Just looking around for further questions. Anybody in the audience? I think I see one in the back. Victor. While we're waiting, can I ask one quick one? Is there a data set that you would like to see in the near future? Is there something that you think the community is close to producing that you would really like to see and has a lot of value?
That's a great question. I'm not sure if I can quickly
okay,
respond.
Sorry,
Yeah.
I'll let Victor ask his question then. I'll ping you about that after.
Yeah, absolutely, yeah.
I'm inspired by the comment about graphics for robots or graphics for AI, and you mentioned lowering the resolution. That's one element, and then adding in these additional modes with sound and so on. I wondered if you could unpack that a little bit for this audience, what this might look like in terms of what the differences are.
You mean from the perspective of graphics systems design?
Yeah, graphics for humans, we're kind of pretty motivated understanding, but graphics for AI or graphics for robots.
Yeah, it's kind of it's an interesting thing to think about, because there's these obvious kind of biases where we can design things in a particular way to work for, say, current approaches in terms of machine learning, and then have a tight loop where we optimize things for that, and it's not good in the longer term. But maybe to answer the question broadly at a high level, the key thing is that for most purposes, data volume is desirable when it comes to machine learning, artificial intelligence. And so anything that can be done to make things faster, scale better across, say, multiple devices, parallelize better, are highly valuable. And that's kind of in stark contrast to the typical real-time graphics setting where you just have these human eyeballs that you're generating visuals for, or maybe audio that goes along with it. So that's at a topmost bit, that's the biggest difference, I would say.
Okay, if there are no more questions from analysts, let's thank them one more time, and congratulations once again.
Thank you, everyone.
And so that's the remainder of the talks and paper sessions for today. But up next we have the online poster sessions, I believe, that are starting or may have already started, because I think
it have already started.
Yeah, we're running a bit late. And this evening we have the conference dinner that's starting at 6:15, quarter after 6, I think.
6:30.
6:30. Okay. So it's a short walk away. We can form groups and walk over in just a little while. It's a 10-minute walk. I think it's pretty warm out. Maybe bring a jacket, but it's not that far. And you can also Google Maps it. It's pretty easy to get there. And yeah, thanks everybody. I hope to see you in just a little bit at the dinner.
The address for the restaurant will be posted on Discord. Okay, so like, and I will send you an email for that, and this so that you found the place. Okay. Thank you.